Well, I think we can get started. We already have like 30 participants who joined the tutorial. So good morning to everybody. My name is Marina Zapater. I am an associate professor in the University of Applied Sciences of Western Switzerland. And today I'm here with some colleagues that I'll introduce to you in a minute. And the goal is to give you a tutorial on how we can use GEM5 and how we can also use full system simulation of RISC-V systems in order to enable the optimization of heterogeneous architectures. So basically, the way in which this tutorial will be managed will be that we will start by having some morning research talks. I'll start by giving a talk, then Sergi Abadal, who is a postdoctoral researcher in Universidad Politécnica de Catalunya, will give us his talk on wireless interconnects. Then Dr. Irem Boibat from IBM will give us a research talk on analog in-memory cores. And then Dr. Alexander Levis from EPFL will talk about in-cache computing. So in the morning session, the goal of the morning session is to give you an idea of the novel architectural enhancements that we can propose. And then we will always be linking this to show how we can simulate these novel architectures using GEM5. And of course, we can obtain accurate results and results that we can trust. So morning will be research talks. And then afternoon, it's going to be hands-on sessions. And for the hands-on sessions, we will have Joshua Klein, who is a PhD student at EPFL, and David Truan, who is an engineer at Asho SSO. And they will be both helping you to run your first simulations in GEM5, and they will hopefully be able to answer all your questions around what is GEM5, how does it work, what are the enhancements that we have proposed, what is GXR5, the new simulator for RISC-V systems that we will be showing you. And we will give you an opportunity to go hands-on on everything you want. So basically, how a bit more about the program. Here is the schedule. We are sticking to the schedule that is published on the HighPeak site. So you can just follow that. Just beware that the way we will do it for the morning sessions is that we will be doing every talk, and after every talk, there will be a 5 to 10 minutes Q&A. Okay, so that in case you're interested in one talk but not on the others, you can just drop in and drop out at the time that the schedule says. So normally, if everything goes smoothly, we will be doing a coffee break around 10:15 for roughly 15 minutes. And then we will just close the session at 12 so that you have plenty of time to eat and then watch the keynote. And we reconvene for the afternoon session at 3. Okay. Then afternoon session. So basically, we will start with a more basic hands-on session on how to use GEM5 and how to use our new, how to simulate RISC-V architectures within GEM5. So Josh and David will be taking care of that one. And as you will see in a minute, we basically will give you a virtual machine so that you can try everything on your own. So everything everything is going to be recorded. In fact, you will see that we will be playing some videos. So don't worry if you miss something, you will have access to everything. So what else? So we will be doing a smaller, let's say, short Q&A after the first session at 4. Then we will do the coffee break. You can always use the coffee breaks to ask questions if you want. So you want to try and catch somebody, go ahead, okay? And then the last session is going to be shorter. It's scheduled 4:30 to 5:30, but in fact, it contains 30 minutes of Q&A. So basically, you have plenty of time to ask questions. And in order to ensure that you can ask as many things as you want, from 5:30 to 6:30, even after the program ends, Josh will stay there to answer all your questions about how to simulate, okay? So given that we're all online and it's not so easy to see people, to get the feeling of people when we are not face to face, I have prepared a small poll, okay? that you can access here at slido.com. And I would like to ask you just a few questions to understand what's your profile and what you're expecting from this tutorial. So I will just drive you to, so just try to connect to slido.com. And I will basically share with you the results. So we will be going into a poll, and in that way, you can reply to everything. Yep. Let's go to the poll. Let me share. 1 second. Okay, let's see if it is the bug again. Okay, here we are. Okay, so you can just connect to the first poll, and we're asking you a very simple question of what do you know about Gen 5? The idea is to be able to fine tune. Okay, that's starting to update. So the idea is to be able to fine tune a bit the way in which we will be speaking or answering questions to you in order to make it more adapted. So it seems, okay, I'll give you a few more time to reply. Let's see how it goes. Okay, cool. Still completing. I'll give you a few more seconds to reply. Okay, in any case, it's not moving too much now. So basically, it seems that most of you know what it is. You've never used it. And another chunk of you, okay, you've used it once or twice to get results for a paper, but not many pros. Okay, that's good because the first tutorial will be, so don't skip. So all the people who answered, I know what it is, but never used it, try not to miss the first afternoon session because there Josh will be showing you exactly how to run everything. And I guess that the virtual machine that we'll be sharing with you will be super useful in these conditions. Cool. So let me ask you then the next question. So what do you know about RISC-V? Okay, it's filling in. Apparently if you registered is because you know something. That's clear from what we see. Okay, so some people, well, that's quite spread. So everybody knows something, that seems clear. Many people know the basics of RISC-V architectures. Some of them a bit more, like a third is deeply involved in research on RISC-V, roughly. Okay, most of you know the basics of RISC-V architectures. Okay, cool, that's good. The tutorial is mostly related to Gen 5, but we will show you how you can apply all the enhancements to RISC-V architectures. We will show you exactly how you can use the RISC-V full system mode that we have created for Gen 5. So I think that's really good. Perfect. And then, ever used Gen 5X, or do you know what it is? Okay, a big no. Okay. Okay. So basically, today, so this afternoon we will be working with Gen5X. So basically, what Gen5X does is that it enhances Gen5 with some new features to make our lives easier. You'll see that during the tutorials. And I think so. This will be a very good opportunity for you to be able to compare versions to see what exactly Gen5 does. Okay, that's fantastic. So thank you for filling in all the three polls. Let's just go back now to the presentation. Okay. Cool. Okay. So basically, as I was saying, the goal for this tutorial will be to simulate architectures, and we will show you how you can simulate architectures from the circuit level to the system level. So the goal will be using Gen5, and we will be showing you why we developed Gen5X to start with, and what is GXR5 and how we can use it to be able to simulate RISC-V architectures. So basically, Gen5X is already open sourced, as you will see. So you can download it and use it freely. And we're giving you a virtual machine with Gen5X pre-installed. And GXR5, so basically today, what we are doing is we're giving you the premiere on how it works. And pre-releases will be available for attendees of the tutorial, meaning that we will basically be giving you access to GXR5 if you wish to have it. Okay. So to prepare for the hands-on session of this afternoon, please download the following virtual machine. We will post that link on the chat so that you have it available. So basically, it's a 10 gigabyte virtual machine. You should have the time to download it. And there it comes with Gen5X pre-installed. And the only thing you need to do is to download VirtualBox and import the virtual machine. In any case, Josh will tell you details on how to do that afterwards. So if anybody has issues on importing the virtual machine, we will help you out. Don't worry. Okay. So far, this is an explanation of how the tutorial will take place. If you have any questions, you can just drop them on the Q&A, and we'll be happy to answer. Okay, no questions as it seems. Okay, so we will now go forward then with the first presentation. So the first presentation is about Gen5X itself and how we can use it to explore architectures. So I will be basically playing a video for the talk. This will be what we will be doing for all the talks. We have pre-recorded all the talks to make sure that everything runs smoothly. And after the video, you will get a chance to ask as many questions as you want. Good morning, and thank you for attending this talk. My name is Marina Zapater, and I am an associate professor in the School of Engineering and Management of Vaud in the University of Applied Sciences of Western Switzerland. So today I'll be giving you a talk on the tools we have been developing in ASHO SSO and in collaboration with EPFL on Gen5X, GXR5, and how we are performing full system simulation in order to explore and enhance heterogeneous architectures. So all this work that we have been doing is a research in collaboration between EPFL and the University of Applied Science of Western Switzerland, and you will be seeing also chunks and pieces of all the research we have done in the talks that come also after my talk.
So first, why doing architectural exploration? So just let's start by a little bit of motivation. So as you know, multi-cores are growing fast and are becoming more performant. So at the beginning, it was enough to just increase the number of transistors on the chip. At some point, we saw that the single thread performance started to stagnate, and we decided to go for multi-core. And what we are seeing now is more and more powerful chips with more and more cores, and even becoming heterogeneous. That is, where we put GPUs, FPGAs, etc., in order to attain even a higher performance. So the thing is that, as you know, computing is more indispensable than ever. Data centers and cloud computing are serving a myriad of new applications. So before, it used to be when we spoke about high performance computing, we were just thinking about gene sequencing, financial simulations, molecular dynamics, weather prediction, typical HPC. But today it's way more than that. We have medical analytics, we have video streaming for like platforms like Netflix, etc., with artificial intelligence and online gaming. So what all these applications have in common is that in the end, they are tackling very huge data sets, and they have some stringent quality of service requirements. They have some real-time requirements. And more specifically, within all these myriad of applications, we know that artificial intelligence, AI workloads, are in all the aspects of our daily lives. And furthermore, they have started to span beyond the data center. So some of these workloads are no longer only data center constrained, but they are also going to the edge. And then here comes the issue. So we need to be tackling efficiently workloads that will be moving from the data center to the edge. And we have to tackle them seamlessly. Because, as you know, today the importance is on creating value out of the data. So basically, our edge devices will be collecting data, will be processing data, and all the data that they cannot process, they will send it to the data center. Which brings up with a new challenge, which is we need to have efficient multiprocessor system on chips, and these efficient MPSoCs need to be on the data center, need to be on the edge, and we need to tackle power, performance, and thermal challenges. So how do we do this? How do we do this efficient, high-performance multiprocessor system on chips? Well, there are two things that we can do. The first one is managing them efficiently. That is, doing some kind of multi-layer hardware-software management, like tuning the frequencies of the cores, like improving the task allocation, etc. But the other one is working on novel architectures. That is, creating radically different new MPSoCs with very out-of-the-box and new architectural enhancements. So in this talk, I'll be focusing on this second part, on the part of the architectural enhancements, and we'll be telling you a bit more how we propose to explore these new architectures. So if you think about how to enhance architectures, many ideas come to mind in order to overcome these two walls that we have today. So today we have the power wall mainly, and the memory wall. And today, not only in my talk, but in the talks that will come afterwards in the morning, we will see a few options to overcome these walls. Specifically, Irem and Alex will be speaking about in-memory computing techniques, or that is, trying to bring the computation closer to the memory, or the memory closer to the computation, in order to be more efficient and to consume less power. And the other technique we'll be seeing today, which Sergi will be telling us, is how we can use faster interconnects, and in particular wireless interconnects, between the processor and the memory in order to speed up computation. So in the end, regardless of the techniques we applied, the challenge remains the same. And this is why we're doing this tutorial. The challenge remains on traversing the hardware-software stack. while obtaining accurate results. Okay, so just keep in mind that new architectural enhancements in the end will be coming from the hardware, device, or technology level. For instance, we might be working on new types of bit cells, new types of memory devices, and what we want to do is to incorporate that into the architectural level. But in the end, what you also want to do is to be able to assess those results, the accuracy of those results, not only at the circuit and not only at the architecture, but at the overall application. So when you run an application from a user, how does my whole stack behave? So in the end, this is the big question that we are trying to solve. It's how do we bring them up the stack so that we can test with real applications? How do we traverse from the technology to the circuit, to the architecture, to the system level? How do we provide support at the software? How do we provide support to run an application, a user application? It can be a TensorFlow, it can be a CNN written in TensorFlow that somebody will be running with all the libraries of the system on top of a Linux operating system. Well, so the answer to our question is we propose to use architectural simulation, and specifically Gen 5. And as you will see, the enhancements we've been working on top of Gen 5, such as Gen 5X and GXR5. So let's speak a bit about Gen 5X. Okay, so what is Gen 5X? So first of all, it's a Gen 5 based simulator in which we have added some architectural extensions. So the name stands for Gen 5 based full system simulator with architectural extensions. And what we did with Gen 5X is providing or trying to provide out-of-the-box simulation of a wide range of architectural extensions, including the capabilities of extending the Gen 5 ISA of an ARM system, putting in cache computing, scratchpads, HBM2s, etc. But it's also a methodology for the optimization of many core heterogeneous platforms. And today I'll be also talking a bit about how we are applying this methodology. So the way we see it, what we need to do is to run user-level applications, whatever application it is, characterize it, and optimize the architecture. And then iterate the loop until we meet certain constraints, the constraints we're looking for. And then we can say that we have achieved an optimized architecture. And also, this is also important, Gen 5X in the end, it's the result of our journey trying to learn Gen 5. So basically, when we first downloaded Gen 5, we did what everybody does, try to download, try to run, see what happens. And then we faced many issues, many things that were not working the way we wanted them to work, many images that were outdated. And then Gen 5X is also an effort of trying to put together a lot of enhancements to make our lives easier when running Gen 5 simulations. So more specifically, it's support enhancements and validation. So first we were looking for scalability. So what we did is we are trying to open source something that is out-of-the-box simulation, a complete environment, a full system simulation that works. We are basing ourselves on the Gen 5 core of August 2018, and we provide working simulations for Intel, ARM32, and ARM64. And then it means that we can run an Ubuntu, that is an Ubuntu system with a decently recent kernel, and where we can even run inside the Linux OS, we can run some containers in case you want to give it a try to virtualized applications. Furthermore, we also incorporated inside the simulator the capability to use gperf, because what we want to do in the end is to characterize how the applications work inside the Gen 5 simulator. And we are providing enhanced checkpointing to speed up the simulation, to stick always to the region of interest, and also hot swapping of disk images in order to enable researchers, PhD students, whoever, to just be able and work faster with Gen 5X. A very important point also that we wanted to do is to validate that everything matches the performance of real systems. Because the issue with simulators, is that you can simulate everything, but what we want to make sure in our research is that the numbers we get are the closest possible to the reality. So how did we do this validation? So basically what we did is to try and match the performance against an ARM Juno board. The ARM Juno board has in-order and out-of-order cores, so we were trying to just play around and match exactly the number of edge units, the number of functional units, execution stages, the latency of functional units, everything, so that in the end we could compare what is the performance of a certain benchmark in Gen 5 and in the Juno board. And what we found is basically that we are able to obtain errors which are below 4% when compared to the execution on Juno. So we mean comparing the execution time of a benchmark in the Juno board, the execution time of a benchmark in Gen 5X, and that difference is below 4% for both in-order and out-of-order cores. So what else did we do? So at that point, we already had all these support enhancements to make our lives easier when simulating. And then the next step for us was to do the architectural enhancements. That is, at least providing to ourselves a backbone for a wide range of extensions. So what are these extensions that we were working on? So the first ones that we will be seeing briefly in this talk, but also afterwards in the talk of Alex, is in-cache computing and hybrid caches. We'll also have 3D stacked memories, and in particular HBM2s, and then scratch parts and extensions to the ARMv8 ISA. How to extend the ARMv8 ISA in detail, it's something that you will see this afternoon during the hands-on tutorial sessions. So let me start by an example case study of how we can find the best architecture for a certain application. And this certain application that we were using is video analytics. So what is video analytics? So this case study is, you can imagine it as running a pipeline in which we do first video streaming. So we do some kind of encoding process, and then analytics on the images that we have encoded. You can think of it as video surveillance cameras, the typical application of video surveillance for smart retail, for smart cities or smart cars, or for traffic control. So you're basically encoding video and processing, doing some analytics, some convolutional neural networks. And the goal here is to show how, by using Gen 5X, we can see how we can use some architectural enhancements, such as in-cache computing or HBM2 memories. So let's start first by the use of in-cache computing. And we start first by seeing how we can speed up the first part of the pipeline, which is the video encoding. So to do this, what we did is we were characterizing and exploring how different cores behave using Gen 5X. So the first thing we tried is, let's give it a try at different types of cores, in order versus out of order cores, to find execution bottlenecks. And the first bottleneck that we found is that the FIR filtering that happens during the encoding exhibits a very good level 1 cache locality, which means it's a very good candidate for in-cache acceleration. In the end, what we are trying to do is simply to analyze which are the chunks that take most of the time and how we can accelerate those chunks. So what does in-cache computing acceleration mean? So Alex will be telling us a lot of details on how this works from the circuit and the technology level, but just to give you a very brief explanation from an architectural system level, what we are doing with this in-cache computing is that we add a little bit of extra logic to the cache, to the L1 cache of our system, in order to be able to perform simple computations. That is addition, shifts, etc. And basically, because the FIR filtering is basically additions, subtractions, and shifts, it's a very good candidate to be accelerated by this in-cache computing. It will allow us to reduce the energy. So what we are looking for is to reduce the energy and to enhance the performance of our system. And we were trying that for different types of cores, at different types of frequencies, and for different types of input videos: high resolution, low resolution, medium resolution. And what were our findings? So basically what we could see is that for both types of videos, low and high resolution, we were able to enhance the performance and reduce the energy of the execution when picking up the right type of architecture. By right type of architecture, it was, for instance, in-order cores with in-cache computing for the execution of the encoding, and we were getting a 15% overall speed up for the application. So this was for the encoding only. What we did afterwards is, okay, what if I go and look into the whole pipeline? The whole pipeline being video encoding plus video analytics. And then we said, okay, we know that this will be also bottlenecked by the connection to the main memory. So what we decided is, okay, so let's go and see how we can build a heterogeneous architecture in which we have regular in-order cores, ARM64 in-order cores, in order to run the part of the CNN. And then we will be using in-order cores with in-cache computing for running the part of the encoding. And then we are connecting this to a high bandwidth memory using the global interconnects. And we will be using an 8-channel memory, 1024-bit bus, and 3D stack DRAM4 memory banks. And we allocate separately the two different applications. So this is a kind of a very heterogeneous system. It has CPUs with and without in-cache computing, and also a very nice memory hierarchy, very fast memory hierarchy. So what we found is that we can speed up the application by an extra roughly 8% for each of the stages of the pipeline. And the interesting conclusion is that both applications benefit significantly from the architecture, because we are basically tuning the architecture towards the specific applications that we want to run. So finally, what we were trying to do in the end with this research is, what we can do is to combine Gen5X with with tools for power and thermal modeling and characterization. So in the end, what we want to have is a full suite of tools to find the best performance, power, and thermal trade-offs for our applications. Then it means that we can use Gen5X for performance characterization and to explore the different architectures. We can combine that with power modeling, either using MacPath or either creating our own models, our own power models, and then just putting that together with thermal simulation using 3D-Eyes, which is also a tool developed at the EPFL. So until here, I told you quite a lot about how can we do this architecture exploration, why do we do it, etc. But probably at this point, you're still wondering, like, okay, but how do you traverse the hardware-software layers? So how do you go from the technology up to the system level? So of course, all the tiny details, you'll see them this afternoon on how exactly what we change and how we change it in Gen5. But let me give you a detailed example of how we can do this using hybrid caches. So this is an example that we have of hybrid caches for CNN acceleration in edge devices, okay, not in servers, in edge devices. And the goal of this research was that basically, edge devices are very much constrained in terms of resources, and even small networks for edge devices can have a footprint of in the size of megabytes. And within that footprint, we know that the weights of a CNN can account for almost 40% of all memory accesses in the inference and have a very high read-write ratio. That is, weights are basically something that is read over and over and over again, whereas inputs is something that tends to be written and read more often, okay? So having this in mind, a research idea came to our heads, which was, okay, let's take advantage of this to try and do something more efficiently on our cache. So now what we are proposing is, instead of having a regular cache, the regular cache has a technology which is the static RAM, SRAM. We're going to use non-volatile memories. So non-volatile memories, like resistive RAMs, They have a large density, but they have a smaller leakage than the SRAM, that is, smaller energy consumption. But their issue is that they have limited endurance. That is, you cannot write to them very often, or you will degrade their reliability. So what we decided is, okay, so let's just propose a system in which we have a hybrid cache, a mixture of SRAM and NVMs. Okay? Good. So this is something, the numbers themselves from the technology level, it's something that we could obtain. But the thing is, how do you put this on the system and how do you simulate this at the system level? So what we decided is, okay, let's design a hybrid cache from the computer architecture perspective. We'll put regular ARM cores, we will put a regular SRAM hierarchy, but we will duplicate the hierarchy just to have a resistive RAM next to our regular SRAM, like this, like what you can see in the image. And then what we will do is, everything that is weights to the neural network, this will go into the resistive RAM, whereas everything that is inputs, it will go to the regular static RAM. And in this way, we will be able to take advantage of the benefits of one and the other. So basically, as I said, for efficiency enhancement, we use resistive RAM for reads, we use the SRAM for writes. And then what we would like to do is something like this exploration. We want to explore for different types of networks, Inception, ResNet, SqueezeNet, for instance, what is the power reduction and the performance gain for different sizes of the cache. So what is the solution to perform this exploration? Gen5X. So in order to bridge the gap from the circuit to the system level and to traverse all the layers in between to end up in the software, what we do is we start from the hardware level implemented in Gen5X. That is, we incorporate circuit level models. These circuit level models can be obtained in many different ways. You will see on the talks of Alex or Irem or Sergi how you can obtain those models. And once we have the per block performance and even power data, what we do is that we will plug that into Gen5. And we will be implementing that into the architecture. So that is, we will create new models, we will create new architectural enhancements, we will change the underlying models of Gen5, and you will see how to do that on the tutorial of this afternoon, until we get, for instance, an architecture of a hybrid cache like the one you see here. That is, we will duplicate the level 1 hierarchy in order to include this hybrid cache with resistive RAM and with a static RAM. Once we do that, of course, we need some OS level support. The way we do it is that we will reserve a region of memory in boot time that we will devote in order to place what we want to place. In this case, the reserved memory chunk will be for the weights of our CNN. And then afterwards, the only thing we need to do is to create a C++ user library for this new hybrid cache that we called Shy Cache, and new functions that will enable me to malloc and allocate the regions that I had reserved during boot time. And once I've done that, I will have my new user library, and I will be able to use it. So I will have an application that will be able to use that user library in a seamless way from the application perspective. This means that you can potentially run any application that you want because you will have all the underlying software support that you need. So you will basically have this full hardware software stack simulations. And you know that this will be accurate as long as the circuit level models that you have developed are accurate. And everything else should be preserving the accuracy. So far in this presentation, we have seen how you can use Gen5X for architectural enhancement to just test and propose new architectures. Of course, as I said, on the tutorial of this afternoon, you will get all the details, all the fine-grained details of how this can be done. So stay tuned for the tutorial of this afternoon. Just to tell you, Gen5X has been open sourced since April 2019. You can download it, you can subscribe to our mailing list, you have the code available in GitHub, you have patches. So in the end, what Gen5X does is it patches the Gen5 installation and works in a very similar way to Gen5. And just remember to check out the VM that we have prepared for you for this afternoon's tutorial. Give it a go, and hopefully we will be able to solve all your questions on how Gen5X works and why is it useful. So just keep in mind that very last thing, our latest new adventure is GXR5. Okay, the goal of GXR5 was to provide full system support for RISC-V, for RISC-V architectures. And you will also see all the tiny details of what is working exactly. Just to tell you very briefly, and afterwards Josh will tell you more details. GXR5, what it does is it's the first Linux-capable full system simulator built into Gen 5. Before GXR5, the support of RISC-V architectures was only on system emulation mode and was quite limited. And as I said, you'll see a premiere of all the features and capabilities this afternoon. So GXR5 will be available, same than Gen5X. It will be available on GitHub, open source, really very soon. But if you want early access to the code in order to start testing everything, just send us an email, send an email to Josh, put me on CC, and we'll give you access to the code given that you have registered to this tutorial. So thank you for your attention, and if you have questions, I'll be very happy to answer. And here you have my contact information. Thanks.
Well, so thank you for listening. Let's now open the Q&A. In case you have questions about the talk, feel free to just either raise your hand and ask, or write it on the chat as you prefer. So there's been quite a lot of discussion about the virtual machine on the chat. Just let me remind you that we have put the link to download the virtual machine on the chat so that you can start downloading it, and you don't need to wait until this afternoon because this 10 gigabytes, we know it's a bit heavy, okay? So just go to the chat, with the link is there, and you can download the VM whenever you want. You can also, as Josh was saying on the chat, you can also, in fact, you don't need the VM if you have an Ubuntu system. You can simply install Gen5X. There's also a manual on how to do that on the link that we have provided to you. So just follow the link we gave you. All the documentation, everything is there, basically. So do we have do we have questions? Not that I see. Yeah, here we go. Let me open the Q&A. So, and somebody was asking, so I'm reading on the chat right now, I'll go to the Q&A in a minute. So any plans for integrating the RISC-V full system support into Gen 5 mainline? Yes, it's a plan. It will be done. We'll give you details on how it's on the current status and how it's going to be our timeline on this afternoon. But yeah, so basically our goal is to be able to incorporate everything into Gen 5 mainline. The thing is that so far we've not yet done it because we want to have a very stable version once we try to do that, or the commits might be rejected. Once we have that, we will be able to integrate everything together. Okay. So let's go to the Q&A. Open question. So could you go more in depth on how software simulation works on Gen 5? As Gen 5 is a simulator, it cannot run it natively. So how do you get performance results? Oh yeah, so I don't know if I really understand the question. Let me try to reply, and if I don't reply correctly, please re-ask. Don't worry. So basically, Gen 5 itself, it comes with ways of telling us what is the stress on the real system. So basically, it gives you performance counters of what is happening inside. So you can collect, for instance, Gen 5 allows you to collect the number of instructions that you have executed, how many of those instructions resulted into a cache hit, cache miss, whatever, okay? So basically, what we are putting together is the metrics that Gen 5 already provides to you, which are quite a few, and allow you to assess how everything behaves on your system, together with extra metrics that we can get from Perf. And also, for instance, if your software, so of course, with any software, if you can just measure the time it's taking, okay? And it's, so I think, did I reply to that question, Amund? Okay, hopefully yes. Otherwise, okay, awesome, thank you. So Roberto Giorgi says, in slide 9, you mentioned 4% difference in accuracy, but what is the slowdown? 4% wait, so what we did there is the comparison of the execution time of one against the other. So basically, we are comparing how long it takes in a real system, what is the real execution time that a certain workload takes in a real system, and what is the reported execution time by Gen 5. So what we are trying to compare is, do we get the same numbers, yes or no, basically. So I'm trying to match the behavior of an architecture. Do I get the same result, yes or no? That's the thing. And then, of course, so if you compare the actual real execution with the execution of Gen 5, Gen 5 is slow. That's it. So it's an architectural simulator. So it's going to be way slower than running it on the real system. That's why the goal is not to use it to simulate something that exists. The goal is to use it to simulate something that doesn't exist, okay? Like, for instance, if you want to quantify, Josh, can you report us, for instance, what was the numbers? So in the latest simulation, the fastest you can go, 1 second of simulation. Can you tell us, Josh, for the CNN workloads, for instance, how long it was taking on the real system?
So if I recall correctly, we actually have an Arduino board in the office that my colleague Yussi Qureshi uses, and he said that for 30 seconds of simulating a benchmark on the real board, that's 30 seconds real time, that equates to approximately a couple days worth of time in simulation. But of course, if all you're looking for is functionally accurate results, you wouldn't be using Gen 5. You would be using something like QEMU, for example.
So just keep in mind that it's slow. So it's not something you can use to run 5 minutes of workloads, basically. So you need to stick to the region of interest. That's why many of the enhancements we did are targeted towards running the specific chunk of code that you want to profile, basically. Okay. Yeah, we agree that slowdown is very important. So Mohammed said, do GXR5 support RISC-V vector extensions? So not yet, we're going step by step. That's the goal, okay? So we are, as of today, supporting the boot and the execution of simple benchmark with GXR5. But of course, the major goal of this research is to be able to exploit the vector extensions of RISC-V. That's the whole point. But what we started by is, okay, let's be able to run any application. And that's already quite tricky. You'll see this afternoon. Let's just support running regular applications, and then we can build on that. So Roberto asked, in slide 12 for in-cache computations, how to make sure that all the data you need is in the cache at the same time. All the data we need will not be in the cache at the same time. So basically the data that is not on the cache will be brought into the cache. Just stick to the talk of Alex, because I did not have the time on this talk to provide all the information on how that is working, okay? We will tell you exactly what happens when you bring data in and out of the cache on the in-cache computing. But basically, the cache in the end will work like a regular cache. Things will be evicted, things will be taken from main memory to the cache, okay? And then if the data that we need for a computation is not there, we'll just simply bring it. Is there a plan to port those enhancements? But in-cache calculation needs to operate in cache only, right? Yeah. So basically, we are performing in-cache computing operations in between different ways of the cache. So we need things to be on the cache. Otherwise, we cannot. So we will need to bring it inside the cache and compute in there. But as I said, we'll show you the tiny details of how it works precisely on Alex talk. So stay tuned to that. So Nathaniel, is there a plan to port those enhancements back to Gem 5? Yeah, as I said, similar for GXR5. We want to put everything back into Gem 5 mainstream. As you know, that's a kind of complex development effort. We need to make sure everything fits smoothly. For the moment, that's why we stick to patching the Gem 5 core, and that's it. But yeah, everything will be at some point into Gem 5 mainstream. Timon, what is the need to use GPerf profiling within Gem 5 simulator application? Gem 5 already provides insight on how the application behaves on the hardware. Yes, so I agree. So most of the things that you can get with GPerf, we basically can also get them from the statistics that Gem 5 provides itself. There were just a few things that were not nicely supported, and that's why we added GPerf. And it was also a way for us to be able to see if we were adding or not adding any overhead on both ends. But yeah, you could just not use GPerf if you don't want to, and stick to the regular counters that Gem 5 is providing for you. So Ruben Salvador asks, are you aware of other similar works that extend Gem 5 towards architectural level exploration? Not officially released. So we know there are some groups, some research groups working on Gem 5 extensions of extending differently Gem 5. They have taken other paths, not exactly the same path that we did. There are many other extensions, like to try and provide Gem 5 with support for communicating with GPUs, with support for communicating with other things, but not precisely what we are doing, which is basically trying to add things. But in any case, the good thing is that it's not that we are providing something that is incompatible with anything else. So basically, any enhancement that works in Gem 5 can work in Gem 5X, because we are respecting the interfaces, so it should be okay. And the last question is from Alejandro. Wait, no, not the last, there's another one. So is it GXR5 also covering the generation of RISC-V SOCs or just simulation? No, we are simulating. So what we are doing is we are simulating RISC-V architecture. So anything you want to add on a RISC-V architecture, if you do, and you'll see that on the next talks, because we will link with the technology. So if you have an architectural enhancement, and you have tested it at the technology level with simulations, with post-layout simulations, whatever, and you extract models, you can plug that into GXR5. That's no issue, okay? But we are not simulating inside Gem 5. We don't simulate at a lower level than that, okay? And then last question, are you aware of anybody using Gem 5X for simulating clusters of multi-cores? Clusters of multi-cores. Wait, careful, huh? Because the moment, so increasing the core count greatly reduces, greatly increases, sorry, the execution time of the simulator, meaning that you have to be very careful with what you do exactly, in the sense that you have to be aware that basically we are so the maximum, if you go, the moment you go above 4 or 8 cores of simulation, then you start getting very, very slow simulations, okay? So just be careful with trying to do that. What do you use to generate the system images? Wait, let me repeat Roberto first. No, 8 cores is not a limit. 8 cores is not a limit. We have been simulating things way bigger than 8 cores, but just be prepared to wait 1 week or 2 weeks to get the results. So normally we try to run things at 4 or 8 cores at maximum, because that's what stays within a decent amount of time. And then we just run very few simulations at 64 core level, just not to be waiting for 2 weeks or 3 weeks to get a result, because it really can go so bad. Okay. Okay. Cool. So I think I missed one question from Jorn. What is the benefit of using Gen 5 over cycle accurate RISC-V simulators like FireSim, which can simulate VR hardware? Okay, so we'll give you more details on that this afternoon again, on why and when you need to use Gen 5. So Gen 5 is middle ground in between cycle accurate simulators and QEMU. Okay, so it stands at the middle ground in which you can simulate at the instruction level, and then it's faster than other simulators, than FireSim, but slower than QEMU. Okay, we will give you more details on how exactly we place that. So all the tiny details on how Gen 5 behaves, speed ups, how does it work, etc. Just, I will ask you to wait until the afternoon, okay? Because we just already jumped over our coffee break. So if that is okay with you, all the tiny answers, all the answers, I know you have many, many questions, and that's super great, thank you. All the questions related to speed ups of the simulator, maybe I think we can discuss them also on the afternoon session, if that's okay for everybody. Okay. Good. So if you allow me, I will close, I will give you a 15-minute break now, because I think you need it, okay? And even if we are 15 minutes late, I think it's not gonna hurt much to just reconvene in 15 minutes, that is at 10:45 for the next session, so that everybody can have time to grab a coffee and you know, and take a bit of a rest, just to recover energies for the next talk. Don't worry, if I missed any question, I'll just check afterwards. If I missed any question, I promise I will answer afterwards. Don't worry, we can just discuss at midday at 12, or we can just keep on discussing this afternoon. So thank you all for attending. Thank you all for the very interesting questions. Let's reconvene in 15 minutes for the next talk. Thanks.
So hello again, it's 10:45. So let's just reconvene the session. So for the next section, our next speaker will be Sergi Abadal, who will be giving us his talk on wireless interconnects for heterogeneous systems. So let's. Okay. So let's start with a talk from Sergi. Sergi Abadal, by the way, is a distinguished researcher at the Universidad Politécnica de Catalunya, and he's our expert on wireless interconnects today. So you will get the chance, like, as always, to see the video, and then we will have a Q&A session with Sergi.
And think wireless interconnects for heterogeneous systems. The talk is going to have three parts. First, we're going to talk about heterogeneous systems. Second, we're going to talk about the fundamentals of wireless interconnects and why we think that they make sense for heterogeneous systems. And finally, we're going to talk about how to simulate and how to integrate wireless interconnects into architectural simulators like Gen5 or any other simulator that you might want to choose. So first, a little bit about heterogeneous systems. Processors are anywhere. You know that, from cell phones to laptops, to data centers, to embedded systems, to appliances, to connected cars. And companies are trying to make them faster, make these processors more efficient, and especially, or even if you have heterogeneous workloads, so you want to make them faster and more efficient always, right? So you have two ways of doing that. First, a general purpose chip, which works well for several workloads. Then accelerators, which work very well for very specific workloads, and they do not work that well for other workloads. And finally, you might want to have something in the middle, which generally we call heterogeneous systems, to those systems that integrate different types of processors, so that they work well in all occasions and they work very well in like AI. So how to build heterogeneous systems? Well, this picture is a good example of how to do that. The Pulp platform, they have several types of cores, several types of accelerators, and several types of interconnects, peripherals, and so on. So whenever you want to create a heterogeneous system, basically you pick those cores that suit you best, you put them into an interconnect, you architect the whole system, and then there you have your heterogeneous system, right? What's the issue of that? That the interconnect is always at the center of these heterogeneous systems, and the communication requirements are generally high. They are always system dependent, so depending on how the system looks like, you're going to have one or other communication requirements. These requirements are uneven spatially, so not all components will need to move the same amount of data, and they are generally dynamic temporally, which means that depending on the pace of your application or depending on which application is being run at different times, then your workload is going to be changing. Right? So how to integrate the interconnect within a heterogeneous system? There are different ways in the state of the art. The first one is just to have a heterogeneous system integrated everything within this single large chip. Communication is through a fast but generally rigid network on chip, and you see the case of Samsung processors used in Tesla cars, in which there's a GPU, there are several AI accelerators, there are processor cores, and there are other specialized components, and everything is put together through a network on chip. Generally, you have high performance because everything is integrated. You have high bandwidth, high efficiency. The generalization is moderate and the cost is high. The reason is that if you want to have a system that works well in another scenario, you have to rewire the entire chip. You have to put, if you want to put another component, you have to rewire the entire chip. And you know that these large chips are pretty expensive to make. On the other hand, there has been lately a trend on disintegrating with chiplet-based architectures. This one is from AMD. And basically, you put the CPU and the memory and the accelerator chiplets and they are wired up in a larger interposer system instead of a single chip. There are different chiplets, and they are interconnected through this interposer. And this communication is via, as I said, via this interposer, which is a bit slower than the chip, but this allows to have different chiplets with different accelerators, different CPU chiplets, different memory chiplets, more specialized kind of architectures, which you can pick and place into this interposer. The cost of that, of building the chips, of integrating the whole thing, is lower. It gives you good generalization because you can have kind of a library of chiplets that you can put together, but the performance is worse than in the chip case because the interposer is lower than the chip, and it's more its energy, it's less energy efficient. So you pay the price of generalization with lower performance. But still, even in the on-chip case and in the interposer case, the problem is that both cases are rigid, and you need to over-provision your system to kind of cover up for all the communication costs of the system. That means that if I introduce a new chiplet, I need to rewire the entire system so that it supports this new chiplet. Good. So the vision of our project Whiplash is to create the next generation of computing systems that are efficient, fast, and flexible. And this will be enabled by developing massively parallel heterogeneous architecture with two main components which are new. One is in-memory computing accelerators, which is kind of contributing to the heterogeneity of the system, and then wireless interconnects, which is basically trying to cater to the communication needs of these heterogeneous systems. Now, let me jump right through to the second part of the talk, in which I try to make the case for wireless interconnects and explain the fundamentals of this idea. So a little bit of background. Basically, the size of wireless antennas scales inversely proportional to the frequency of the wireless transmission. So Wi-Fi works at 2.4 or 5 gigahertz of radio frequency. But for instance, in 5G, there has the proposal of using the band of 60 gigahertz, in which the antennas already fit within the chip. So the concept of on-chip antennas was born, and you can see an example here on the left, in which you see a typical structure of a chip with bulk silicon dioxide, and then the other part of silicon dioxide, and how using the materialization layers you can design an entry point, and then you can design a dipole which is integrated within the chip. And beyond that, when you go at higher frequencies, even beyond the 60 gigahertz, you start having the possibility of integrating more than one antenna within the chip or within a computing system. Moreover, the transmitter and receiver circuits that you need to drive the antenna, they are also integratable into a chip, or in other words, on-chip transceivers are also a reality. And this is an example at 65 nanometer CMOS, working at 240 gigahertz, transmitted at 60 gigahertz per second, consuming this amount of area and power. And there are prototypes that this has been built, so we can put more than one antenna within the chip, and we can put more than one transceiver within our chips. So the proposal that we make at Whiplash is that we will integrate on-chip antennas and transceivers into chiplets, so that we can create a communication network that is wireless through the processor package. This network is global and reconfigurable, and will always complement the wired network. And the way that it works is that if each chiplet has an antenna and a transceiver, the transmitter just takes the information from the chiplet and modulates it, radiates it. This information will propagate through the package, will reach the receiving antennas, and which will demodulate and give this information to the receiving core. So we claim that this has a moderate cost, so it has an increased cost over interposer because you're adding RF circuitry, but it provides an excellent generalization and high performance in heterogeneous systems. This is because the advantages of wireless are that it provides a layer of low latency. So system-wide, you can achieve a latency of a few nanoseconds, which is not achievable with interposers or other technologies. It is inherently broadcast because When you radiate, these signals will reach everywhere in the packet, so you can make broadcast transmissions out of this wireless interconnect. And you have what we call system level flexibility. It's something that we will explain later. The keywords of this wireless technology is that it's generally less efficient than other technologies. In general, we can talk about a few picojoules per bit. And it has low bandwidth. Since everyone is kind of sharing the same channel or same small set of channels, the overall bandwidth is not that very large. And we can talk about the order of 10 to hundreds of gigabits per second. So when we talk about flexibility, we say that, okay, now imagine that we have this system in which the processor, memory, and accelerators, they have to go at the speeds of 30, 10, and 20. But now imagine that we have to introduce another chiplet because the system has changed and we need to reconfigure the whole thing. What we can do is just to, as long as this chiplet has an antenna, we can make it participate in the communication now. And if the communication needs of this system change and now the processor doesn't need to communicate and the others need to communicate more often, through medium access control protocols, since the communication is global, we can make this change of bandwidth per chip. So now, in some sense, this gives us some flexibility to adapt to the communication needs of the heterogeneous system. So when designing this wireless network or this wireless interconnection network, we generally look at a simplified version of the wireless protocol stack. We have the architecture, the network layer, the link layer or MAC protocol layer, and the physical layer. And to put it into a graphical example, everything that is inside the core and the memory that tell you how to use the wireless interconnect, it's going to be architecture. Anything that interfaces the cores with the wireless network is going to be network layer. And then the MAC layer and the physical layer are inside the transceiver, which basically tell you when to transmit and how to modulate the information that you transmit through the wireless. So we're going to go through all of them, just explaining a little bit of the fundamentals of them. So architecture, how does the architecture leverage the wireless network? This is a decision that requires architectural expertise of the processor of the heterogeneous system. And if you want to evaluate it, you need an architecture simulator like Gen5. The output of this layer is going to be execution time and system energy or power. But if you want to use wireless interconnect, you need to go lower in the stack. Some examples of architectures that we have been proposing in the past that make use of the uniquenesses of wireless. First one is WiSync, ASPLOS 2016, which basically we use the wireless network for synchronization. Basically, we have small broadcast memory to store logs and barriers of our programs. These small broadcast memories are kept coherent through the wireless network in a separate way from the cache coherence protocol. And the way it works is that every write that we do to these memories is broadcasted and updated every time that we make a write across all the broadcast memories, so that everyone keeps a coherent copy of this data and all the reads that we do to this memory are local. Just by introducing one antenna per core and having a broadcast wireless network at 20 gigabits per second, and just changing a small part of the code because it's only logs and barriers, we have a bit average of 1.41 speed up over /2 and parsec. So, well, we saw that from the architecture perspective, it made sense to have wireless, right? So we went further ahead and we extended this idea to any kind of data that's latency critical, not only logs and barriers. And we created Replica, which is ASPLOS 2019. And with the same kind of characteristics and more effort from the programmer to fit everything within the broadcast memory, we had an average speed up of 1.89. Then we realized, how can we do that without having to put a burden to the programmer? Like the programmer doesn't need to be aware of how much of our wireless data are we putting in the broadcast memory. We created WIDIR, which is this extension of the coherence protocol that uses wireless for some aspects. And again, one antenna per core, wireless channel at 20 gigabits per second. We achieved 1.28 average speed up, but no impact on programmability whatsoever. So this was a good thing. So we saw in the end that wireless made sense in shared memory systems. Then into chiplet-based accelerators, we also tried to answer if wireless made sense in those accelerators. So can we scale out DNNs thanks to wireless interconnects? That's what Vienna is our proposal. We have one transmitter in memory, in this high bandwidth memory, and then one receiver in each computing chiplet. And just with a wireless bandwidth of 64 gigabits per second, we achieve these large speedups, and we achieved some energy efficiency by just reducing the transmission time, reducing the inference time of the accelerator. So just a few examples that support the idea of having wireless in architectures. So let me go down just quickly over the network layer. Basically, are the wireless interfaces connected to the NAC routers, or are they connected just to the network interface at each core? This is the kind of decision that you make at the network level. How is the traffic routed in the case that we connect the wireless interfaces to the NAC routers? Do we steer a lot of traffic to the wireless interfaces? When do we steer that traffic? So this is kind of the decisions that you make at the network level. For that, you don't require an architectural simulator, but you only require an NOC simulator. But if you want to model wireless interconnects into the whole architecture, maybe you need to also integrate wireless into the NOC simulator that this architectural simulator is using. In the end, if you only model up until here, you will have the network latency, throughput, and energy and power of the whole network. As I was saying, there are basically two main trends. On the one hand, you can have separate planes. You integrate the network interface, the wireless interface into the network interface. So whenever data comes out of the core or memory subsystem, you will choose if you want to go through the wired network or you will go through the wireless network. So the main decision is how to steer the traffic at the cores, let's say. And then the other main trend is, okay, we put wireless into the network, not at the network interface, but into the network, so that the data will come out of the core, will go through the network interface, will come into the different routers, and the routers will decide if they just send this data through the wireless or keep it through the wire. Next is the link layer. The main thing is the MAC protocol. Basically, we have to be aware that overlapping transmissions in time will be lost. Then, how do I schedule those transmissions to avoid losses? And that's what the MAC protocol is doing. Basically, this requires a network simulator to evaluate. Doesn't have to be a NOC simulator, but again, if you want to include it into your architecture simulator, you might be using the NOC simulator that is included in Gen5 or your architecture simulator. The output of this layer is where the wireless latency, throughput, and energy and power. Basically, there are two kinds of trends in MAC protocols. On the one hand, you have collision-free protocols like token passing, in which basically you try to avoid collisions at all costs by making sure that only one node will be able to transmit at the same time. In token passing, only the node that has the token can transmit. This way, we don't have to handle with handful collisions. Collision-free protocols are generally simple and provide higher throughput, but on the other hand, they don't scale to larger systems. On the other hand, we have these contention-based Wi-Fi-like protocols in which nodes contain, for example, the MAC protocol tells you when to transmit with the hope that you will not collide with other transmissions. If there's a collision, the system has to detect that, and you have to kind of remedy that situation by having some exponential backoff or something like that. The advantages of that kind of MAC protocols is that they have generally low latency and they scale well if they are well designed, because they adapt better to varying volumes. They are not fixed, they are not static. And finally, we have the physical layer, which is how do we modulate and radiate the information that we have at the cores. For that, to simulate that, you require only MATLAB or hardware models of your transceivers and antennas, and the output is raw data rate, error rate, and power consumption. Basically, you take those models, there's those hardware models or these MATLAB simulations, and you integrate those models into your architecture simulator just to simulate this physical layer. Okay. At the physical layer, I will only mention that for this wireless interconnects idea to make sense, we need 10 gigabits per second or more or less 1 picojoule per bit, and wireless a bandwidth density of 100 gigabits per second per millimeter square. But let me also tell you that technology is advancing well in that direction. These pictures, basically each of these points is a wireless transceiver, and we have data rate over power consumption, so data rate over transceiver area. And if we are in this area and in this area, we should be fine. So basically technology is advancing well in that regard. So the wireless interconnect idea should more or less make sense. So now that we explained everything about that you want to know, at least on the fundamental level about wireless interconnects, let me just go quickly over how you can try to simulate wireless in Gen 5, or as a matter of fact, any other simulator that you might want to use. Okay, so this is the same picture that we had before. We have architecture, we have network, we have MAC, and we have physical layer. Okay, so to analyze the impact of wireless interconnects in heterogeneous systems, you will need an architecture simulator, period. So you might want to use Gen 5, implement wireless into Gen 5, and then use to simulate your regular architecture, your heterogeneous architecture, or whatever architecture that you might want. Okay, so how to model the wireless network? The easiest and less expensive and less accurate way to do it is basically you have a system bus with a configurable latency and bandwidth. So you say that the wireless network has a configurable latency and bandwidth, and you try to adapt your models to the reality of wireless interconnects. But this generally won't work because it doesn't take into account contention, doesn't take into account some of the particularities of the wireless network. So we don't want to do that. So the other way to do that is using the tools that Gen 5 and other simulators they provide. And one of these tools is Garnet, which is integrated in Gen 5 for a long time now. And now I think they have released the version 2.0, which has heterogeneous kind of network on chip integrated. So you can use the blocks and the tools that these network simulators they are giving you to try to emulate what wireless would, how wireless would look like. Okay. So the thing is that what Garnet does not model wireless connectivity, and HeteroGarnet, which has been released not long ago, might support it in the future, but the reality is that right now Gen 5 does not support out of the box wireless. So alternatives to that is you try to interface Gen 5 with a network and chip simulator that includes wireless, which might be Noxim. You might want to check Noxim, which includes support for wireless interconnects, or you implement your own version of wireless within Gen 5/Garnet. And that's what we're going to talk now. How you modify Garnet or how you modify Gen 5 to introduce wireless. And at the architecture level, basically you modify the architecture in Gen 5, and you might want to check the other talks in this tutorial on how to do that. Okay, you basically say when am I using wireless? Is it in my heterogeneous in-memory cores? Is it in my regular cores? We'll see, right? At the network level, you basically modify what Garnet understands as network interfaces or routers to include the possibility of connecting a wireless interface, and you have to modify the routing protocol to be able to steer traffic to the wireless interfaces. Then at the MAC protocol, basically the MAC protocol has a queue and implementing some delays when transmitting. And finally, at the physical layer, you have to model collisions and model when you're going to have successful transmissions. So that is fed back to the MAC protocol, which will update the delays that these messages will suffer in transmission. Okay, so what is in Gen 5? How to kind of implement the detection of collisions and successful transmissions. Basically, what we do is consider that each core and memory, each wireless interface has its own queues, and then we implement kind of a large bus or a large switch in the middle, which kind of models the wireless channel. Right? This wireless channel is a centralized module to which all wireless interfaces are connected, and can be using this whatever bus model or switch model or any custom model that you want. Actually, HashMap is a good way to model a wireless channel. So how do you think of a successful transmission? Basically, the MAC protocol tells you when to transmit. Imagine that this core and this other core want to transmit. Basically, the MAC protocol tells you to transmit. So imagine that core 1 is able to transmit. Transmitting is basically in Gen 5 sending a copy to the wireless channel. Then at the end of one cycle, the wireless channel checks that there is only one active transmission. That means that just one person is transmitting, which means that this is going to be a successful transmission. No collision leads to a packet replication at the wireless channel, which means that since wireless is broadcast, this might reach everyone. So basically, this kind of bus or wireless channel that you are modeling, it should be replicating this packet to the all outgoing ports of this wireless channel. Okay. Then no collision leads to packet replication of the rest of wireless interfaces at the start of the next cycle. And the reason for doing that is that wireless transmission may have this very small propagation delay until the first bit arrives to all the receivers. Okay, so that other transmitters will always be able to know that there is an ongoing transmission and will not transmit on top of this other ongoing transmission. And then the wireless network stays like this for a few additional cycles, which is basically modeling the transmission delay. And transmission delay is basically the packet length divided by the wireless speed. After the transmission delay, the packets will be removed from the channel and from the wireless interfaces, and the cores will react to that delivery of information the way the architecture has been programmed to do. Okay. Now, let's imagine that we have a collision, right? So now let's imagine that core 1 and core 3, their MAC protocol tells them to transmit at the same time, okay? Both at the same time. If basically, whenever the wireless channel checks if there was only one transmission at the same time, it will see that it was not. So basically, the channel will signal the collision to all the participating cores or all the cores, depending on how you want to implement. This signaling will be sent to the receivers, depending on how you model your MAC protocol, either instantaneously or at the end of the transmission, depending on how the MAC protocol works. Okay? So whenever the receivers, they receive this signal saying, okay, there has been a collision, this has to be submitted to the MAC protocol, which will react to that collision. If the MAC protocol tells you wait one cycle or wait a random amount of cycles, the MAC protocol will do that to the transmission and will try again to transmit. And in this case, imagine that core 1 tells, the MAC protocol tells him to wait one cycle, and for core 3, the MAC protocol tells him to wait 5 cycles. The core number 1 will transmit first, everything will succeed, then core 3 will transmit after that delay and will succeed, and everything will be fine. So you see that there's a way to do successful transmissions and one way to detect collisions. With that, you should be enough to model wireless interconnects into GEM. To model energy, basically you collect the statistics on the number of collisions that you have made and the number of successful transmissions that you have been able to perform. Then with those numbers, you calculate the average number of collisions per correct transmissions, and basically with this model, you should be able to model the energy. Basically, successful transmission is the energy consumed at the transmitter plus all the energy consumed at all the receivers that are receiving this transmission. The energy of a collision is basically a fraction of a correct transmission, and the average amount of energy for a correct transmission is the energy spent in the successful transmission plus all the times that there was a collision with the rest of transmissions. With that, it should be enough to model the energy of the wireless interconnect. So conclusions: heterogeneous architectures call for versatile solutions at the interconnect level. Wireless can respond to those needs with low latency, system level flexibility, and inherent broadcast capabilities. And evaluating the impact of wireless interconnects in heterogeneous architectures requires some tweaking of Gen5 or your architecture simulator of choice. Basically, you take cycle accurate simulation of collisions for latency and a statistical model for energy. Acknowledgement, this project, WIPLAS project, check it out if you like to know more about wireless interconnects. And this is the team that is participating in the project. You can find us at the web, Twitter, LinkedIn, and ResearchGate. This is all. Thank you.
So thank you, Sergi, for the talk. It's time for Q&A. I see there are already some questions on the Q&A board. So Sergi, the floor is yours. Feel free.
Okay, thank you, Marina. Good. So I see a few questions. There's a question that I answered through the question and answer in written form, but let me re-ask that so that everyone can check. So is there any quality of service issues modeled by in the wireless network? I imagine that even accounting for a small bit error rate in crucial exchanges like logs can have a large performance impact. So this is by Timon. You're completely right. So any error that can happen in any communication might be very harmful. But we have to take into account that wires also have errors, right? But the thing is that the bit error rate for wires is very small. So generally, the impact is also very small or very, very infrequent. So what we do is to model wireless to similar bit error rates. And that has a cost in terms of power. So you have to transmit a higher power to have enough energy over signal to noise ratio to have this error rate very, very small, but it can be done. And then you can treat errors in the same way that you would do in a wired interconnect or in a multi-core processor. So that's pretty much what we do. The other thing, the good thing is that the wireless can also allow you to tune the power that you want to consume, so that if you want to afford to have a higher error rate in sacrifice for power, so be more efficient but have more errors, you can do that, and approximate computing can be a good friend for that. So I hope that answers the question. Second question by Timon as well. What is the crossover point in micrometers or millimeters when the wireless links have lower latency than wired links? Of course, this is not easy to answer because it depends on many things like the technology node. But you know that as you go deeper into the few nanometers technology nodes, the interconnects become, let's say, more expensive. So going global or going broadcast at the interconnect level in wires, it's very expensive for the small technology nodes. So that's one thing. But if we consider like 40, 65 nanometer CMOS, people have shown that starting at 5 to 10 millimeters, wireless starts becoming lower latency and more efficient than wires. Of course, this also depends on the number of routers that you have in between, right? So if you want to break down a long link because it's inefficient into smaller links that have routers in between, I talk about wires, then each router is going to be adding latency. So that becomes a better case for wireless. And finally, broadcast is where wireless makes more sense because it's in wireless, but in wires you have to replicate the message many times. So I would say that those are the main issues to take into account for this crossover point. I hope this answers, but I'll be happy to follow up to those questions if you have more time afterwards. Antonio Portero asks, thanks for the presentation. Can you comment the trade-offs with respect to an optoelectronic solution instead of a Wi-Fi solution in terms of power consumption, security, bandwidth, size of the silicon? Okay, that's a very complete question. I'll try to do my best in short time. So in power consumption, optoelectronics also works better because the energy is guided, so you have less losses, of course. In security, it's more secure because energy is guided, so you have to tap into the wire if you want to listen, let's say. In terms of bandwidth, it's better to have optoelectronics because you can put several wires in parallel or several waveguides in parallel, so you have more bandwidth. Size of silicon, it depends on how the network looks like. But on the other side, so security is not an issue in wireless because packages are generally enclosed. So if you want to hack into the wireless within the package, you need to be inside the chip. So somehow you need to have a hardware Trojan or something that is inside the chip attacking from the inside. And that's hard. So that can also happen for any other interconnect solution. In terms of power consumption, I would say that depends. So if you want to go long range and you want to go broadcast, wireless makes more sense. Why? Because optoelectronics or wires, in optoelectronics, you need, the way this is architected is that you put a laser into the chip and then you distribute this laser power over the people that want to talk. That means that you have to dimension everything to the worst case, and broadcast is the worstest of cases. So In broadcast, optoelectronics becomes expensive because each of the nodes has to take part of the light of the laser, and that's a lot of power. So there are trade-offs. So that's for the architects to tell, okay, this is the best solution for me, this is not the best. But I would say that all of them, they have their pros and cons. And size of the silicon, it depends on how many transceivers you want to put. It depends on the speed, it depends on several things. But I don't think there's a clear winner. So I hope that answers most of it. Then let me go for this voted one. Kevin Martin, thanks for this very nice presentation. Thank you. In your HPCA paper, you use SST simulator. Can you discuss the differences with Gen5X and advantages and disadvantages? Well, good question. Good question. I don't think it's a matter of SST being better than Gen5 or worse. I think it was just a matter of that the people that were working on the cache coherence protocol thought that it was easiest to change in SST in the way it was written in SST. It wasn't a matter of Gen5 or SST being better in one thing or the other. In terms of wireless interconnect modeling, it was the same. So the way of modeling, it was the same in SST than in Gen5. So there was no difference. In the end, what I would say is that whatever that goes best for your architecture simulation, go for it and then implement wireless into that simulator because it's very similar in all of them. I don't know if that answered the question, but I can refer also to the experts that work with SST and can tell you more about it. Okay, so Luis, Teres, sorry, we have started to talk about NOC to flexibilize about 20 years ago, and just during the latest years, some NOCs have been a reality. When do you expect to have the complete technology ready for these antenna-based intra-chip communications? Good question. Good question. The technology is ready, and people, and let's say that there's no barrier preventing you to try to take the antenna transceiver, put it into a package, interface it with digital, and building it, right? But we are still in a phase in which we have to do the application pull, right? Showing that the architectures make sense with wireless, putting all the system level simulations together so that we can convince actually the people that can have the money and time to actually make the engineering effort to build that. So I would say that if there's the interest, this can be done next year, but we're working on that, of course. To see that in a commercial product, I would say that it's more like 5 to 10 years. If there's people wanting to do that, which we do, but of course it's not immediate. As you see theory and practice, then there's some gap. And another question by you is, to get maximum gain from this inter-chip wireless, most of the components in your system on chip must have such technology. Could it be a barrier to really apply this technology? I'm not sure I'm following. Do you mean that all of them, they have to have like 45 CMOS, or they have to be all CMOS? And can you clarify that? Okay, if not, I would say that you can do that. There's integration, ways to integrate different technologies in the same chiplet, but I would say that I don't really know if that would be a barrier. I have to think about that, but I don't think it will be a barrier, because in the end, you can have different technologies, but the transmissions, the antennas and the transceivers, they work at a frequency, right? And as long as the modulator and antenna, they work in the same range of frequencies with the same specs, it should be fine. So if you refer to that, you can do that in silicon germanium, you can do that in silicon, you can do that in graphene if you want, but as long as they talk into the same frequency with the same modulation, they should be able to understand each other. So that change of technology shouldn't be an issue. Marina, how much time do I have? Can I just go?
Yeah, it would be good if we can finish So just take a couple more questions, 2-3 minutes if you
Okay.
can answer fast. Because I would like to start the next talk by 11:30.
Yeah, sorry, I'm taking too much time, yes.
No problem, no problem. It's very good that people is asking so many questions. It's
Yeah,
awesome.
I appreciate it. In wireless, there is an issue of bandwidth. So how do you deal with the large data transmission? And also about the synchronization with the router frequency. As the wireless might be slow, suppose you send 1 megabit of data smoothcasted. This will also increase the peak latency for the system. Yeah, there is a trade-off. If you need to broadcast 1 megabyte of data, and that's a lot, and you think that wireless is gonna take a lot of time, you might wanna parallelize. So you take a chunk of data through the wireless, and you take a chunk of data through the wires. Of course, the wireless broadcast is not as efficient as in the wireless, but if you do it in parallel, you're kind of increasing the throughput, right? But it's true, wireless, it's not thought to for very large chunks of data. So large chunks of data parallelized with the wires. If you need to send short control like packets and you need low latency for that, use wireless exclusively for that. But that's an architecture question, really, actually. So, but that's a good question. So I would say make the most of the wireless whenever you can. And David, will the additional noise introduced by the wireless transmission not be problematic? No, because basically, so RF transmissions occur at 60 gigahertz or beyond. That's that's different from the 1 gigahertz, let's say, clock frequency. So let's say that the RF doesn't impact on the digital. So you can work those independently. So really, I don't think there's going to be additional noise. Maybe there's an increase of temperature, but that's also for the architects to see how to prevent that and how to deal with that. Good. So I'll be happy to follow up on any of those questions. So feel free to write, and I'll do it during the next presentation. I can write more answers. So thank you everyone for asking.
So thank you, Sergi. And again, thank you everybody for asking and for being so active. As Sergi said, we'll be doing our best to just type the answers to all your questions. And also by the end of the session, you can stay and you can ask as many things as you want. But let me just go now for our next speaker, who is Irem Boibat. So Irem is a postdoctoral researcher in IBM Research Europe. And she's our expert today on analog in-memory computing. So let's do the same, and we will just be playing Irem's video presentation, and afterwards we go for Q&A.
Hello to all. This tutorial talk will focus on in-memory computing-based acceleration for AI. My name is Irem Boibat, and I'm part of the in-memory computing group in IBM Research Europe, which is located in Zurich, Switzerland. First, I want to present why we need new approaches to computing to accelerate our workloads. And next, I will give an overview of in-memory computing as an emerging paradigm and talk about how computation can be performed with charge-based and resistance-based memory devices. We will then turn our attention to how in-memory computing can be leveraged from a systems perspective. In particular, we will look at how cache and main memory can accommodate in-memory computing, and how standalone accelerators with in-memory computing-based cores can be constructed. Finally, we will talk about ways to address the imprecision arising from the analog mode operation. Various advances in hardware, such as the widespread use of GPUs and progress in the algorithmic domain, all led to the AI revolution in the past few decades. AI systems now manage to reach and even exceed human performance in various cognitive tasks, such as image recognition, strategic games, and reasoning. AI is transforming our lives, yet it is facing significant computational challenges. The energy consumption associated with current AI workloads is difficult to sustain. For instance, running a deep learning model requires considerable hardware resources and can take up to weeks. If you look at the environmental footprint, the electricity consumption when training a deep neural network is equivalent to the electricity consumption of a person over 3 weeks. And the carbon emission is comparable to 2 weeks of carbon emission of a person. And this is just the cost of training a single model. Today, state-of-the-art deep neural networks are composed of hundreds of layers and millions of weights, requiring a massive amount of computations and memory. The availability of new datasets in the size of gigabytes in a wide range of new domains have enabled the increasing adoption of deep learning to solve a large set of problems. But at the same time, this only aggravates the challenge. Now, if you take a closer look at what the main memory, at the main bottleneck, now we see that transferring data from the memory is 3 to 4 orders of magnitude more expensive than processing the data itself. And this is due to how our computers are constructed since the 1940s, where the processor and memory are physically separated, and data has to be constantly shuttled back and forth between the two. A key research question is, can we come up with a better computing approach? In memory computing breaks away from the conventional way of computing by performing certain computational tasks in place in memory, such that memory and processor are co-located. Efficient computing can take place using the physical attributes of the memory devices, their array-level organization, and circuitry. Computing in this manner offers significant advantages owing to two key properties. First, the costly data movement is reduced. And second, because memory devices with its circuitry is now your key computation primitive, millions of operations can run in parallel in memory computing systems, resulting in reduction in application runtime. Now, the key distinction here is for memory computing is that at no point during computation, the memory content is read back and processed at the granularity of a single memory element. Now, memory stands at the core of memory computing. And one class of devices that we see for memory computing is the charge-based memories, such as SRAM, DRAM, and flash, where information is stored in the presence or absence of charge, hence charge-based memory. However, a new class of devices has also shown significant promise. These are the so-called resistance-based memory devices, or often referred to as memristive devices, where the information is stored in the atomic arrangements or in the orientation of the ferromagnetic layers. Phase change memory, resistive random access memory, and magnetoresistive memory all belong to this group. Now, when you are choosing a memory technology for a specific application, access time for retrieving the data, access time for storing the data, how many devices the data can be switched on the device, the device's area and energy footprint, and the technology maturity are all key metrics that play a role. Several logical and arithmetic primitives can be realized using both the charge-based memories and resistance-based memories. For instance, here I depict how a bitwise logical operation can be performed with SRAM. SRAM cells lie at the intersection in such arrays of intersection of rows and columns, or as we call them, the word lines and the bit lines. To perform bitwise operations, first, you charge the bit line and bit line bar to the supply voltage VDB. Next, you activate both of the word lines at the same time. According to the memory content you have in these two SRAM cells, whether they're configured as 00, 01, 10, or 11, the bit line and bit line bar are going to discharge at different rates. And depending on what is stored in the cells, you are going to observe a different VBL and VBL bar. Then comparing this voltage, let us say VBL, with a reference voltage, any threshold, then, for instance, an AND operation can be detected if you have a 1, 1. Now, matrix vector multiplications can be realized within memory computing as well. And this is rather important for the domain of deep learning, as vector matrix multiplications make up a huge part of these workloads. In this particular configuration, SRAM cells are used in conjunction with a capacitor, again, lying at the intersection of word lines and bit lines. Now, how the multiplication is done in 3 steps is the following. First, step 1, you close the switch between the word lines and the capacitors. And according to the input value you apply, you charge the capacitor. In the second step, you close the switch between the SRAM cell and the capacitor. And according to the content of the SRAM cell, you are going to discharge some of the capacitors. And the third step, you connect your capacitor to the column or the bit line, and there will be some charge sharing. And at the result, you are going to take a look at the final voltage across these bit lines. And this is going to give you the result of your matrix vector multiplication that you decipher from this voltage. Now, the second class of devices that I want to talk about are these resistance-based memory devices. They're often referred to as post-CMOS devices or memristive devices. Now, in comparison to the previous category of devices where you store information as a charge, here the information is stored in the atomic configurations or the orientation of the ferromagnetic layers of these devices. Different atomic configurations or different orientation result in different resistance values. Applying a low voltage, you can read the resistance values. And when you apply a large enough voltage pulse, then you can change the atomic orientations or the or in the case of MRAM, the magnetic layer configuration. What makes this class of devices very attractive is their non-volatility and their scalability below to 40 nanometer node. Since this class of devices are less known in comparison to the conventional charge-based memories, I want to give a bit more insight onto one of these devices, namely the phase change memory. We experiment quite a lot with phase change memory in our lab in Zurich. Now, a phase change memory device is composed of a top electrode, a bottom electrode, and phase change memory sandwiched between these two. The phase change material can be found either in the crystalline phase, the low resistance phase, or in the amorphous phase, a disordered and high resistance phase. And you can alter the phase configuration of the devices by applying set and reset pulses. What is very attractive about PCM, apart from the set and reset states, is you can achieve intermediate phase configurations. Hence, you can store more than 1 bit of information in a single device. Our studies have shown that matrix vector multiplications with PCM arrays can yield precision equivalent to 4-bit fixed point arithmetic. Now, let us look at how logical operations can be performed this time with resistive memory devices. The devices again stay at the intersection of word lines and bit lines. The input is applied as voltage to these devices. When you apply voltage, a current will be generated according to Ohm's law, reversely proportional to the resistance of these memory devices. Then the currents running through the devices are summed on the bit line according to the Kirchhoff's current law. And when you compare this current with a reference current, you can perform AND operations. Hence, this is how you do computation in the current domain. A matrix vector multiplication can be performed in a similar manner, where the input is mapped to the input voltage, and then the matrix elements are mapped to the conductance values, which is the reverse of the resistance values. And one thing that is very attractive about this topology that's here on the right is, assume instead of supplying voltages to the word lines, you provide them to the bit lines. And instead of reading currents from the columns, you read from the rows, from the word lines. And with this configuration, you can perform a matrix vector operation using this time the transpose of the matrix. And this is particularly important for deep learning training, as the backpropagation stage involves the transpose of the weight matrix. So in my slides, I highlighted some of the logical and arithmetic operations that you can do with SRAM and PCM. However, other mentioned technologies and further computational primitives are also possible. Yet I won't be able to address all of this due to time restrictions. We have now covered the basics of in-memory computing, and now I want to focus on how in-memory computing can be utilized in computing systems. One way is that the memory hierarchy, namely the cache and the main memory, can be modified to support in-memory computing. In the next talk by Alexander Lewis, there will be more detailed insight on in-cache computing. Furthermore, accelerators can be designed, which are composed of one or more in-memory computing cores attached to the CPU via the system bus. And in-memory computing can also be integrated to the processor in various ways. Here I want to point out that exploring how and where components can be integrated into computer architecture is exactly why we build and use simulators such as Gen5. SRAM-based caches can be enriched with peripheral circuits to perform in-memory logical operations, as shown in the figure. Computing in this manner reduces the data movement between the cache and the CPU. However, the size of the cache may limit how large you can choose your operands to be for certain operations. The main memory, DRAM-based, memristive-based, or even hybrid memories, can be equipped with in-memory computing capabilities. The advantage here is that data can be directly accessed without utilizing the system bus. The challenge with computing in a memory hierarchy is that when you add the in-memory computing capabilities, you should not affect the conventional mode of operation of these structures, and you shouldn't bring a significant overhead. Again, more on in-cache computing will be covered in the next talk. In-memory accelerators are especially attractive for deep learning workloads. These accelerators are typically composed of multiple interconnected in-memory cores, and weight layers are mapped to different in-memory computing cores, as shown in the figure on the right. At the heart of the in-memory computing cores is the memory array of unit cells. The core contains peripheral circuits as digital inputs are converted into voltages for inputs, and analog output results should be converted back to the digital domain for further processing. The core may contain a near-memory digital block, which can implement simple functions such as additions, multiplications, shifts, multiplexings, and data conversions. For neural network implementations, the nonlinear activation can also be addressed in this block. Last, the control unit ensures proper functioning of the core. Custom in-memory accelerators allow further design optimization for applications. For instance, bidirectional data flow can be supported for training workloads. Core-to-core communication fabric enables pipeline implementations without install. And a wider range of digital functions can be implemented when cores are used in conjunction with local CPUs. The big limitation of in-memory computing is the imprecision arising from the analog mode of operation. And this is the last thing I wanted to discuss in this talk. In conventional memories, the memory content is read back and digitized individually. Therefore, many sources of imprecision can be avoided. However, here you perform analog computation, and device non-idealities and circuit limitations are there and reduce the precision of operation. More specifically, contributing to the low precision are the limited data representation precision of devices, process variations, randomness, noise, IR drop, and data conversions. One way to address the imprecision at the hardware level is to employ novel device designs. For instance, it has been shown that with an alternative design, PCM arrays can perform scalar and matrix vector multiplications with 8-bit precision, 8-bit fixed point precision. Another hardware level solution is to represent the data or weights in the case of deep learning with multi-device units. The devices of a unit can have the same significance, or they can have different multiplicative factors associated with them so that you represent a number in a radix n system. The input can also be broken into bit positions, which are then applied to the array separately. On the system level, one can leverage a mixed precision computing approach, where you perform the bulk of computation on low precision in-memory-based units. And high precision digital units computes the precision critic part of the algorithm. And finally, custom hardware-aware algorithms can be designed such that the imprecision of in-memory computing can be tolerated. And this brings the end of my talk, and I want to give a brief summary of what we have discussed so far. In-memory computing is an emerging computing paradigm where you use the physical attributes of memory devices to perform computations in place in memory. You can realize various logical and arithmetic primitives using both charge-based devices such as SRAM, DRAM, and flash, as well as resistance-based memory devices such as high-charge memory. In-memory computing can be leveraged at various components of the computer system. In-cache computing can reduce the data movement between the cache and CPU. If you are computing within memory-based approach in the main memory, the data can be directly accessed here without utilizing the system bus. Custom in-memory accelerators can perform tasks with significant speedups, and integration in-memory capabilities with the processor gives access to the rich digital functionalities. The analog computation imprecision is one of the big limitations. However, this can be addressed with various techniques, ranging from novel device designs to multi-device data representations, mixed precision implementations, and hardware-aware algorithms. I would like to acknowledge the in-memory computing group in IBM Research Europe, along with other groups of IBM Research Europe, other labs of IBM, and our external collaborators.
So thank you, Irem, for the nice talk. So it's now time for Q&A. Are there questions from the audience to Irem that you would like to ask now? I don't see anything right now on the Q&A page.
So it either means the presentation was clear or not clear at all. So I hope it was clear.
Either it was super clear or okay, no questions so far.
If there are questions, I can still answer in written form or take them at some point during the day. So if you have, just don't hesitate.
Yeah, maybe one thing we can do is that given that we are a bit tight on the schedule, Aram, if we can do precisely that, if the audience comes up with questions in the meantime, maybe you can answer them in text or right after the talk of Alex, so that we can proceed a bit forward with the next talk. Is that
Sure.
okay?
Yes,
Okay.
sounds good.
Thank you. Thank you very much then. Okay. So then we will be proceeding with the last talk of the morning. This last talk of the morning will be by Alexander Levis about in-cache computing techniques and emerging technologies. So Alex is a postdoctoral researcher at EPFL, at the Embedded Systems Lab, and he's our expert on technology circuit level for in-cache computing. So let's share the screen and play the video. We will do the same, and afterwards we do the Q&A session.
Hi everyone, my name is Alexandre Levis. I'm a postdoctoral researcher in the Embedded System Laboratory in EPFL with Professor David Atienza. And today I'm happy to participate to that tutorial on how to use Gem5 to explore architectures, and I will be giving you an overview of how we can use emerging technologies and architecture to improve the performances of architecture, and how we can explore systems and how we can make the link between circuit and architectural exploration. So what's the context? So the context is we have new technologies coming in like artificial intelligence, we have new constraints coming in like the global warming, and so this pushed experts to believe that there would be a fourth industrial revolution the same way there was the first ones. And this is going to change the society toward a more innovative, sustainable, inclusive society where people could trust the ecosystem. And this relies on the idea that the new ecosystem will be based on collaboration between systems and chips, and this system will be able to take decentralized decisions. So this may seem a bit obscure, but if we go back to some industrial fields like personalized healthcare or natural language translation, autonomous driving, lifestyle monitoring, these activities used to be managed by people with experience and training. And the idea is that thanks to these new technologies, we can adapt the systems to do this task. And so you see the issue coming right away. It is that this needs to be done with a controlled energy budget. So the way we do it today is simple. We leave all the complex computation to be done to data centers. So basically, what we give to the data centers is every task we do not want to do locally because it's too hard, we send it there. And so this brings up a bunch of constraints, particularly on privacy, on security, on latency, on network availability. And you all know that, for example, if you have your diabetes monitoring system, you do not want it to wait for the network before being able to do a measure, or you do not want the power to take over your pacemaker. So this brings up one question, which is that, so what you see on the top right of that graph is basically the new methods that cloud providers have to set up, basically putting their data centers in the polar circle or underwater to make sure that they can control the heat dissipation. And so this idea brings up two questions. The first one is we want to compute locally what doesn't need to be moved, connected to these privacy, security, latency, network availability constraints. And the other one is we want to leave the complex computing and relaxed deadline to the cloud, so that we only send to the cloud things that we need we need to do there, and so that we are not bothered with it locally. But then these things bring up a bunch of questions, and the first one is how do we fit a complex machine learning workload in a device that could have a power budget of the order of the milliwatts? And in data center, how do we keep the energy consumption under control? Because we're gonna do, and we already do, more and more tasks there. And so for the state of the art, for example, artificial neural networks, we know that training them is something extremely expensive. So from that perspective, one way to improve current architecture is to say, let's first look at the architecture. So we have a processing unit, we have a cache hierarchy, we have a memory, and these kind of architectures are not specifically adapted to data-centric application because we spend our time moving data from the top to the bottom and from the bottom to the top. And so we have a huge energy wastage, first due to data movement, and the second one is due to the fact that we have quite a bit of static data, particularly in neural networks, that we don't specifically want to move, but that we want to keep. And so because the data is there, then it's leaking. And so we have a lot of wastage because of that. So there are two possibilities that we are exploring. And one is simply to say, let's just bring more computation inside the cache. So these are these small red boxes that you see on the right inside the memory. And the other one is let's bring in some non-volatile memory. And so with these two, first we can do SIMD-like computation because we can compute a lot of things in parallel inside the memory because we can bring a lot of these small red dots in the memory of computing. The second one is because we can compute the things where the data is, we do not need to move the data too much. And the last point is, thanks to these non-volatile memories, we would be able to reduce largely the leakage and so mitigate this leakage that was killing previously the architectures. So here's the outline of the rest of the presentation. So first I will present an architecture which is a Blade, which is an in-memory computing architecture we are developing in the Embedded System Laboratory of EPFL. And then I will give an overview of how we can integrate emerging NVMs in edge systems through hybrid caches. So when I'm talking about in-memory computing, so the idea of in-memory computing is to take some compute, bring it inside the memory, and then do the computation where the data is. But then just to clarify a bit, when I'm talking about in-memory computing in that talk, I'm not talking about in-memory computing with NVMs. I'm talking about in-memory computing in cache. And as caches are usually made with SRAM, then I'm talking about in SRAM computing and particularly relying on the technology technology called bitline computing. And bitline computing consists of accessing two word lines in a SRAM memory array. So on the right, what you see are memory cells. And so we access these two red horizontal lines. And when we access these lines, then we get a no operation on the bitline bar and an end operation on the bitline. And so we do the computation on the bitline. The issue with that is that when you access two word lines at the same time, you're basically shorting two memory cells that are not designed to be short. And so you have a risk of corrupting your data. And so what you need to do if you still want to do computation with standard SRAM is that you have to reduce your word line voltage. And so you end up reducing your performances. One turnaround for that is to say, let's use cells that are larger, like 10 TSRAMs. This way you have read ports in each of the cells, and so you are not having this risk of data corruption anymore. But then what you end up doing is basically going in a 2-ax graph like that, where on one hand you have density, on the other one you have performances. And so if you want to go the first solution with high density cells but reduced performances, you end up being on the bottom right. And if you use the larger cell, you end up on the top left because you indeed take back the performances, but you lose the density. And our idea when we were thinking about Blade was to say, is there a way that we can take the butter and the money and go on the top right? So this way we keep the high density cell and we also have the full wall line, the full range on the wall line, and so we can keep high performances and high density. And this is how we came up with the Blade, which is Blade for Bitline Accelerator for Device on the Edge. And the idea is to say, let's not take one read port per cell because we do not need it. Let's just take one read port per group of cells, and this group of cells, we call it a local group. So in that case here, we have 32 cells, one local IO that makes the link with what we call the global bitline. And so we have groups of 32 cells with a little read port for each of them. And whenever we want to do an in-memory computing operation, like I was presenting before in the previous slide, then we do it between cells that are in different local groups. So in the end, what we have is a high density memory, which is based on a regular subarray organization, because this local group architecture that I'm presenting here is not something new. It's something really conventional in memories because you cannot make bit lines that are too long for many reasons. And thanks to that, it is then ready for low power and high performance technologies. And I will come back to that later. So the organization of Blade is pretty standard. So based on if you look into a standard memory architecture like you see on the left, so you have subarrays and you have a cache controller, and then each subarray is composed of an array controller, some decoders, drivers. Then you have the memory array and the bitline logic, and our memory array then is composed of these local groups, which is the part called LG plus the local I/O. So we have here 4 local groups with their local I/O, and we have a modified bitline logic to do some operations. So the local I/O, the memory array by itself is composed of these local groups. So we have a world line 0, world line 1 here. And so if we have these states in memory, so here we have 1 and 1, so in A2 and in B2, and we pre-charge first of all the local bit lines and the local and the global bit lines to 1, and then we activate the world lines. And so as you can see on the left, the bit line is connected to the internal nodes, so the bit lines are discharging, then in turn discharge the global bit line, while on the right side it's not being activated. So the global bit line on the left now holds the NOR operation between A2 and B2, while the global bit line on the right holds the AND operation, and by NORing these two outputs, we can get an XOR operation. So these NOR gates on the bottom is actually inside the bitline logic. But then what you can see is that with our approach, we can still do the same operation, and we did not have to modify NOR to reduce the voltage in the periphery. So we can keep high performances without modifying the architecture. Then if we look into the bitline logic, then what we have this multiplexing logic on the top, which is basically related to the associativity of the memory. So basically, the more the associativity, the more you want to have multiplexer, the wider is the multiplexer here. Then we have a carry-ripple ladder that allows us to do additions. And then we have an operation multiplexer that can select between shift, add, or any bitwise operation that we would like to do. And then we have the write back and communication with the outside of the memory. So overall, we can do bitwise operation and also a worldwise operation add and shift. And by chaining add shift, we can achieve MAC operation. And these operations are the basic of a lot of things that are needed at the application level, particularly for data-centric applications. So then what we did is that we simulated that architecture. So we took a 28 nanometer CMOS bulk technology node. We designed a 64 by 256 memory array, which is pretty conventional in terms of subarray in SRAM. We consider high density bit cells with low voltage threshold periphery and RVT array, equivalent parasitics, because we do not want to spend too much time simulating that, but we still want it to be accurate. And we run variability simulations to make sure that our simulations are accurate. So in terms of parasitics, what we do is we have been designing an equivalent model for the parasitics on the decoder, the driver, the array, and all the bitline logic to make sure that our simulation framework is accurate. And then to have a more visual and some area estimations, we actually designed the full memory. And so what we show is that we have less than 10% of area overhead due to the bitline logic that we had on the bottom. So then we simulated the memory array, and so we evaluated the performances versus the memory supply voltage. And so what you can see on this graph, which represents the frequency versus the supply voltage, we represent the top, and then on the bottom, the dotted blue line is basically the blade in which we do operation within the same local group while reducing the world line voltage. And so we compare it to state-of-the-art papers, and so we show that we have the same performance with that than with the state-of-the-art, which means that our architecture is realistic. Then when we simulate the blade architecture when doing operation between the local groups, we end up with the green, the gray, and the brown blind. And so what we see is that at full VDD at 1 volt, we have more than 2.5x performance gains compared to state-of-the-art. And one interesting point is that we can push down the voltage down to 0.6 without any optimization. As we do not have to reduce the world line voltage, we can still have operation until 0.6. It can be noted that we could also optimize that architecture to go to ultra low voltage operation, but this was not the goal of this work. Then what we did is we took that architecture and we started exploring how it would behave if we start changing the amount of world line, the size of the local groups, the amount of local groups, the size of the bit line, etc. And out of that, what we designed is a library of blade subarrays that we can simply pick and that we can model then in the architectural simulator. So basically what you see on the right is a graph in which we show that each of the architectures based on how they behave in terms of energy, delay, and area. And so depending on our need, we can pick one or the other so that we can select it and evaluate it inside the Gem5 simulator. So the next step is simply to say, okay, so let's now integrate Blade inside Gem5 and evaluate how much performance gains we can have thanks to it. And this is what we did. So we compared it with a Neon coprocessor, which is a SIMD coprocessor, to have a fair comparison. And we simulated 3 benchmarks, a cryptography benchmark to evaluate bitwise operation, and 2 one video processing and one CNN layer and one convolutional layer of a CNN in order to evaluate the performances on real applications. So I'll only be focusing on the 2 last applications because these are the ones in which we have nice trade-offs to discuss. So for the video filtering application, basically what we show here is a cycle count with the bar graphs versus the input image size. And on the right, we see the line is basically the performance comparison between Blade and the reference with the Neon processor. And what you can see is that the gain range up to 6x, and there is an interesting trade-off that appears between the associativity of 2 and the associativity of 4. And so basically when the image width is smaller than 1024, the associativity of 4 gives better performances, while when you get to 496, the associativity of 2 brings more performance. So the reason is, and that's you can see it on the left, the difference between the associativity, as I was mentioning before, is the size of that multiplexer. So a smaller associativity means that you have more bitline logic, but you also have less capacity in your memory. So you have more computing capability, but more evictions. And so this is explaining this trade-off that you see here in the graph. And when focusing on a convolutional layer acceleration, again, on the left, we plot on that graph, we plot the cycle count with the bar graph and the performance gain with the solid lines. And so the blue line represents the performances gain of a 32 kilobyte blade compared to an architecture with a Neon coprocessor, while the black line is a 128 kilobyte blade versus the Neon. And so what you see is 2 interesting optimums, one for the 32 kilobyte on a 32 pixel plane, and for the 128 kilobyte, we have an optimum at 64 pixel input. So basically what it means is that the 32 pixel fits in the 32 kilobyte blade. However, when you get to bigger inputs, then it doesn't fit anymore. And then there is a lot of data movement between the L2 or the main memory and the cache. And so what it means is if you want to consider a bigger input, then you will need to consider a bigger memory. But then one would say, okay, so let's always take the bigger one. But then if you take a bigger memory, you have to pay more leakage, which means that depending on what you want to target, and that connects with the previous slides, depending on the need and on the application need, the memory will have to be designed on purpose or reprogrammed to fit with the needs in terms of application. So the next step for us is simply to evaluate this architecture on silicon. So that's what we did with our colleagues in ETH. So we designed a 32 kilobyte, we designed 2 16 kilobyte blade macros that we integrated with a Pulp processor. And it is one of the first implementation of an in-SRAM computing architecture, and we hope that we will be able to get some results at one point with it. Then we did also some optimization with Blade. So we've been exploring, so I'm not spending too much time on that because it's just for you to have an idea of what can be done with it. But basically we evaluated how we can improve the computation by modifying the local groups. So what we did with what we call these embedded shifts, we have also a multiplication accelerator and we have some energy and performance gains with it. And then we also evaluated how Blade could behave if now we start integrating what we call hybrid local groups, which means that we fit it on top of the SRAM local group with resistive memory. We validated that we can have functionality, and then we designed a cycle accurate simulator that allowed us to evaluate the performance gains that we could potentially have with networks such as FluxNet or MobileNet in that case. And so the idea would be that at one point we can get results, and the same way we did like with Blade, with the first person version of Blade, simply take these into Gem5 and continue exploring the gains that we could have. So that was for the in-SRAM computing part. So now I'm going to be describing you briefly how we can integrate NVMs in caches and how hybrid cache can be useful to go again from the circuit to the architectural exploration level. So one of the big challenges of neural networks, to link with my introduction before, is that first we have an extremely limited area power budget in these low power devices. And the other thing is that even these small networks, they have memory footprint in the order of megabytes. So if you have megabyte of weights, then what it means is that you're not going to have a megabyte of cache. So you will need to move the things from in and out. And so you may have an issue with your data movement at one point. So one idea is to say, okay, so let's look at the read-write ratios and the percentage of reads that we have in memory. And so if we take a look, for example, at SqueezeNet network, here we see that the weights, they have a read-write ratio which is higher than 100, and they represent 40% more or less of the read accesses. So how can we take advantage of this high read access and read-write ratio to improve the performances? And one solution is to go for a hybrid cache. So the idea is to say, let's make a memory which is half SRAM, half NVM, and let's evaluate how this behaves in the system level. So the first thing is to say, okay, so let's take an NVM. So which kind of NVM can we take? And so even though resistive memories are not yet industrial, there is a bit of information that can be extracted from the state of the art, particularly ISSCC papers that are usually giving data out of actually fabricated chips. And so in that case, we took this paper plus a bunch of internal information plus some other papers, but we mainly rely on that work. And so what you can see here is that if you go beyond 50 nanoseconds of write access, your error rate when you try to write the memory is going to be really low. So we consider 50 nanoseconds as a good target for this memory. Then what we did is that we made a hybrid cache in the L1 and L2 with dedicated tag array for each of these. And as we are doing deterministic data placement, so basically we will choose to put the weights directly in the NVRAM or in the SRAM, depending on what we want to do. I mean, depending on the data. So basically the weights will go to NVM and the activation will go to SRAM and other variables will go to SRAM. And so this way we have no overhead when accessing a word. So I'm not describing all the software framework. I will let you go to the paper. So in the next slide, I have the title of the paper, so you can get it and take a look at the paper if you're really curious about it. But as you noticed, I'm a circuit person, so I'm not going too in the details of the software here. So basically what we did is that we implemented the ShyCache, which is the name for our framework in Gem5. And we evaluated the performances with, again, a 28 nanometer technology. So for the SRAM, we took partly some internal results in state of the art, and for the MRAM, we took the one I was mentioning before. And then we evaluated 3 different networks, Inception, ResNet, and SqueezeNet, which range from 4 megabyte to roughly 150 megabyte. And we evaluated the performances that we get with these. So we have from 1.3 to 1.7x performance gain and 5 to 5.5x power reduction by going from a conventional cache to a hybrid cache. And in terms of aging, that is and endurance, that is the graph that you see on the right, there is an interesting trade-off that appears in the way that if your ratio of NVM, if you have a small amount of NVM compared to SRAM, then you're basically trashing your NVM because you're bringing in data and you don't have enough. But then when you increase the portion of NVM, you're reducing the aging of your memory. So basically by increasing the size of the memory, we increase the performances in terms of aging of the memory, but then until the point where we only have NVM, and then of course we degrade again the aging of the memory. So what we need to get out of that is that there is an optimal configuration which depends on the application case, because that graph on the right will be different if you consider another application. And depending on what you want, and that is what you can see on the bottom left. If you want to optimize performances or power or endurance or trade-off of these, you will have different configuration of ratios between your NVM and your SRAM, and they will give you different performance or power gains, basically. So as a conclusion, I presented first the blade, which is in cache computing architecture, which goes from the circuit design to the architectural level and shows both circuit and architectural gains and cross-layer trade-offs. And then I also presented you the hybrid cache, shy cache for neural networks for edge devices, which is also a design that goes from the circuit to the application and highlight cross-layer trade-offs. So thank you for your attention, and if you have questions, feel free to ask.
So thank you, Alex, for the nice presentation. We already have a couple of questions on the Q&A board. One, in fact, is both for Irem and Alex. So maybe let's get the first one from Kevin Martin, which says, how is data alignment and allocation in memory is performed? So Alex,
can you hear me?
Yes, we can hear you.
Okay, excellent. Yeah, so on that question, basically there are two axes where we can answer. So the first one is on the hardware side, the other one is more at the architectural level. I mean at the application level. Basically for the hardware side, you cannot just take a memory and do in-memory computing that way. So what we do is the first element is the controller. So we have a controller that ensures that whenever the data is coming in, and so we do operations inside the blade, we make sure that first data are in different local groups, because one of the constraints we have there is that we cannot make an operation between any line, because that is something that would require you to have this, what I was describing before with this control, or at least ensure that you can do operation between lines. And this is too hard to do from a circuit side aspect. So that's why we have first this constraint that we can bring up, propagate up to the control level. Then we have, when you say alignment, probably that you're referring to the way alignment. And so here there are two aspects. The first one is that indeed in the first version of Blade, we had no way to perform operation between ways. So basically this multiplexer I was mentioning, data would only need to come from the same way. And then at one point I talked about enhancement that we have on blades, and so that we have been introducing there the ability to make operation between ways so that we can mitigate issue on the way alignment. And then once you have all that constraints, you can go up to the management this way, then at the application level. And so I could discuss that, but as it is a work that we were actually doing in close collaboration with Professor Zapater, maybe if you want to answer on that part, maybe you're going to be more accurate than myself.
I think you made the point of the question, but in any case, what is happening in the end with Blade is that we, as I said, so this is somehow linked to one of the questions that I got also from my talk, right? So we are just gonna bring everything. So we are trying to preserve everything in the most similar way to a regular system with a regular cache hierarchy. It's simply that we will be marking which data is already on the cache. We'll be flagging the data that is already on the cache. And basically we are adding extra logic to the control of the cache. So there will be a cache controller that is a bit more intelligent than what it was before, and that is marking the things that are coming inside. So basically, in order to perform an operation, what we are doing is we are making sure that everything is properly allocated, that has arrived to the right line of the cache. If it's not, we will request to put it there. And once all the operations are there, we know that, okay, it's correct, we can perform that computation, basically. So that's what's happening a bit behind the scenes from the architectural perspective. So I guess we managed to answer. If Kevin's not convinced or we're missing something, just type that and we'll keep on answering. No, it's not mapped by hand. No, That was the goal. Not to. So we wanted not to do manually as few things as possible. That's the whole. That's the challenge basically. That's the challenge. Yeah. Okay. Then the next question is both for Irem and Alex, and it says that it seems we will move up to bank to computation in memory. How would this change impact in the current processor architectures? That's a good one. So I'll let you discuss, guys, on that.
You want me to open the discussion maybe on Blade? Yeah. So one aspect of it is that indeed we're moving up some operations that we used to do in the processor. We're now doing it in the cache. And yeah, so at the moment, one of the first thing that could come is simply to say, okay, so when I'm computing on the cache, my processor is just waiting. But then that's indeed something which is yeah, of a good interest for the architecture exploration. Yes, indeed. That paves the way for more complete answers, I guess.
Yeah. So on my side, it depends on how you want to leverage the memory computing. So if you, for example, want to build your own accelerator and just attach it, then there won't be much change. It will be like attaching an ASIC or an FPGA or an to the system. Now, another option is, how Alex answered how you do the in-cache computing. Then you have, control logics and so forth. Now, another option is, if you really want to do, for the integration to the processor is an option, and there's a work from EPFL on that. I reference also I give that, and then in that case, if you want to complement with some memory or some logic, then of course you have to think about how you're going to fit ISA, and more on this stuff will, I guess, be covered in the actual.
So in fact, I think, let me maybe, given that there are no more questions, let me maybe go a bit further on that, because this is a very interesting, so this question is maybe key to what we are presenting today, in the sense that, so there are many options in which you can connect an accelerator or a device that accelerates something, right, to the computer architecture. And the most traditional one is basically you just plug it in to the system bus, right, and you get along with it. And when we start needing Gen 5 and this kind of simulators is when we want to deeply intertwine something into the computer architecture. Because at that point, we get into a lot of issues, as Irem knows, right? So when we want to work with analog in-memory cores, for instance, we have to find the best place to put them. So yeah, so an option would be just simply plug it into the system bus, but an option is just make it more intertwined. Put it next to the ALU, put it next to the register bank. So where do you put it exactly, and how do you put it exactly? And that, well, I maybe you can give us some more insights on that, but that really gives us, that becomes a challenge. Where do you place your analog accelerator? Is that, Irem?
Yes, exactly. So that is correct. And you also have a lot of challenges associated with technology, right? So if you want to have, for example, something integrated further into the processor, you have to think about, yes, how are you going to change the architecture? How are you going to change the ISA? How are you going to accommodate the additional area you need? How large of course can you do? Which kind of technology you go for? So Alex, I think you highlighted very well. There are technologies which are very amenable to read, but not right. So then you have a lot of questions, let's say, involving the technology level. Then, as Marina said, where are you going to integrate the course? A lot of things on placement. How are you going to accommodate it in the instruction level? And then it builds up on this side. So this is, I would say, research, very interesting. So we are also.
So I would say, so maybe to wrap this up, I would say that if you see, so and you've seen this in the morning, right? So in all the morning, so we are putting together the expertise from researchers that are more at the technology and circuit level and that are able to say, hey, this occupies this amount of area, this takes this amount of time, and this takes this amount of power, with the expertise of people more at the architecture and system level that say, okay, but then I need to put this next to a RISC-V system or next to an ARM core, and these are the constraints that the architecture brings. So this is the whole goal of this architecture exploration we propose to do, and of the joint research at the technology and system level. The fact that we start from models validated at the technology and the circuit level. And in that case, so Irem or Alex will say, oh no, just don't do this. It's never gonna work. Or just do it this way. This is how it works. And then at the architecture level, we can make sure that we plug it in somewhere that it makes sense and where we're not gonna be killed by data transfers or things that we didn't think about, basically. So I hope, Luis, that we answered. Okay, good. So are there any other questions from the audience? Doesn't seem so on the Q&A board. Maybe the audience is hungry because it's sort of...
They definitely are.
Okay, so then the morning session, we're gonna be ending the morning session now. We will reconvene at 3 p.m. with the start of the afternoon session and the hands-on tutorials, okay? I will be closing the Zoom until 3. So if you have questions, just keep them, write them down, don't forget them, and we'll be able to answer to you again in the afternoon session. So have a good lunch and see you afterwards. And thank you very much all for attending. Thank you for the panelists for the very nice presentations, and see you in a bit.
Yeah, Marina, just a small question for the panelists.
Yeah.
Before we all leave, maybe we could maybe take a picture of us, at least the panelists, so that we can maybe communicate around the iPic panel on social media.
Cool.
Would that make sense to you?
Makes sense. Let's turn on the cameras.
I put a poll this morning.
Should I change?
No, it's okay. No, you haven't seen my pants, that's why.
I don't know if you're in the video there though.
Yeah.
There. The video is there. That's midday.
We can maybe fit in a
moment in life.
In worst case, we can do it this afternoon. It was just that I was wondering, as we are already here.
Maybe we can do it at 3 p.m.
Yeah.
Okay.
Yeah. Okay. So let's do then.
Okay.
Okay. See you. Bye.
Thanks everybody for attending. See you now.
As we said before, so that we can take a picture, and then I need to jump in the call with IMEG.
Yeah. So I just started the webinar.
Yeah.
So yeah, I just started the webinar so that people can start joining. And we wait a few minutes for everybody to join.
Just a Swiss stereotype. I'm eating some. While I'm working from home, I need to keep, the mood up.
We finally have some sun in Yverdon, so no need for chocolate today.
Well, we have sun as well,
Okay, so 11 people connected, but let's give a few more minutes for people to connect. Not yet 3, so okay. So given that we have all the panelists here, maybe it would be a good moment to just, if you can all turn on your cameras, we can take like a quick group picture, you know, to publicize the event and these things.
Yeah.
Josh, we don't see you.
Let me restart just a sec.
Sergi, will you also take the picture? We both take it.
Yeah, I guess
Okay.
if we all try to take a screenshot, we should manage.
Yeah, okay.
Do you want to test something like intro slides or something, or do you want to take it like this?
I could not hear what you said, Mary.
Yeah, I mean,
Oh, sorry. Is it better?
Yeah.
Yeah.
Do we want to test something like a high peak or your brochure or something maybe, or do we want to take it like this?
So I was basically thinking on taking screenshot and probably putting it on the Twitter and the LinkedIn if you want something like that.
Okay.
But up to you guys.
Okay, there it goes.
There we go.
There you go. So let's take a quick screenshot.
Awkward moment. Okay, I got one.
Do you see me or oh, yes, I think.
Yeah, we see you. We see you.
But do you see me horizontally?
Yeah.
We see.
Like the good way.
No,
No, vertically. We see you vertically.
I actually see two Davids.
Okay, yeah,
There is
because
actually
I joined from my PC as well, but I think I'll stick to my phone. I think I'll be okay like this. But on my PC, I see me on the wrong side. I do know.
Guys, I really need to leave, so.
So guys,
Sorry.
if you took screenshots, okay, so we can share that.
Yeah, and then you can make a composition if you want. Yeah. Take the best of us. And then...
Yeah.
Okay, so awkward
guys.
moment finished. Sorry, thank you attendants for waiting for us to take a picture. I think it's good for publicity of the HiPeak event in any case. So, okay, now let's start with the afternoon session. We have 31 people right now. So basically, let's maybe start. So we are sticking to the schedule that I showed this morning. So basically, we will be starting with the hands-on sessions and with the basic or more basic first tutorial, in which we will be showing you how to use Gen5X and also how to simulate RISC-V systems. Before we start though, maybe Josh, you want to make a point about the virtual machine to see if all the attendants have managed, or to provide a bit of insights on how to manage with the VM?
Sure. So if you were having any issues with the VM, basically how you import it over is, in this case, I'm using VirtualBox. So you would select new, and then you would make sure to hit use existing virtual hard disk and make sure you just navigate to whatever folder contains the virtual VM. And that should be it, really. But let me know in the chat, I guess, if any of you are still encountering any issues, and I can try to help you troubleshoot during the lecture.
Okay, for the moment, I don't see any comment neither on the Q&A nor on the chat. So basically, we'll get started with playing the video. So don't hesitate to write questions on the Q&A board while the video is playing. The reason for making a video is because some parts of the tutorial also are quite slow, so it's better if we show them on video directly. But really do not hesitate to write on the Q&A. The moment we will try to be replying on text, and then during the Q&A session, we can again repeat on the most important questions, and you can re-ask if we didn't solve your question properly. So let's go for screen sharing for video sharing. Here we go.
Hello, everyone. My name is Joshua Klein, and I am a doctoral student at the Swiss Federal Institute of Technology in Lausanne, Switzerland, or l'École Polytechnique Fédérale de Lausanne. Today, I'd like to introduce you to Gem5X, as well as premiere our Gem5 extension for RISC-V full system simulation. This session is the first in a two-part tutorial series here at HighPeak 2021. This first session is aimed at those who do not have or only have very little experience with Gem5 and are interested in the practical aspects of using Gem5 for their research. I would say that if you're already familiar with Gem5 and or Gem5X, but you're learning how you use these tools to optimize architectures, that you should take an extended coffee break and come back for the second session. In this first session, I will introduce you to both Gem5X and GXR5, walk you through your first benchmark run, and then cover some useful techniques and features you can utilize to improve your workflow and productivity. In the session that comes after the coffee break, I will explain how you can extend architectures in Gem5X and GXR5 for architectural exploration. So in case you missed the earlier lectures, let us briefly cover what is Gem5 and why would you use it? So as a system-level computer architect, I am interested in the performance and energy ramifications of rearranging, extending, or modifying existing computer architectures to address the gap between memory and compute performance, otherwise known as the memory wall. In particular, my research is focused around RISC instruction set architectures and integrating emerging in-memory compute and near-memory compute technologies for AI applications. As a result, I need the ability to quickly prototype, reconfigure, and simulate new computer architectures while also obtaining valid performance statistics. So as visualized in this graph, if I try doing my work with HDL and an associated simulator such as Verilog with Vivado, I will get extremely accurate performance results with respect to real hardware. But as anyone who has worked with HDL will tell you, I will have a lot of overhead, both in terms of the development and verification time of the new architecture, as well as running high-level applications. On the other end of this graph, I could use a functional simulator such as QEMU, which will provide me with functionally accurate results very quickly, but because intricate hardware subroutines are not implemented or simulated, I cannot rely on QEMU to give me accurate performance statistics. And therefore, I need something in the middle of this graph here, something with just fast enough simulation speed that I can still obtain valid performance statistics so that I can prototype and explore architectures quickly. And so this is where Gem5 comes in. Gem5 is a highly modular and extensible system-level computer architecture simulator, and it represents a middle ground between the aforementioned simulators here. So what is Gem5 exactly? Gem5 is a discrete event, cycle-accurate simulator that models computer architectures as a set or series of black boxes with latencies and attributes, all connected by various buses and ports as defined by a configuration script. So while it is not as fast as QEMU to provide you with functional results, the latencies and system configurations in Gem5 can be tuned to match that of real hardware, and thus you can get performance statistics representative of said hardware within a small margin of error. Furthermore, these performance statistics can be put into a custom and validated power model to then provide good energy results, all while being much quicker to develop, verify, and simulate relative to HDL. So in addition to being cycle accurate and event driven, Gem5 is also highly modular and extensible. Defining a system configuration, things like cache sizes, what devices sit on the system bus or your SoC, what CPU models to use, etc., are all defined in Python scripts. And then these Python scripts use models implemented in C++ to interface. Furthermore, the models in ISA microarchitectures are all segmented, so it is possible to reuse the same hardware model for multiple ISAs. So to summarize the capabilities I highlighted, Gem 5 comes with numerous features right out of the box. It supports multiple instruction set architectures, or ISAs. Its CPU models, including both an in-order model and an out-of-order core model, are ISA independent. And Gem 5 comes with numerous memory and device models included, things like DDR3, DDR4, cache, etc. Gem 5 also has two modes of operation, syscall emulation mode, otherwise known as SE mode, and full system mode simulation, otherwise known as FS mode. SE mode is only used for running and verifying user space binaries, so if you want accurate performance results, you have to use FS mode, which simulates everything from underlying hardware components to your kernel to your file system. However, all components do not necessarily work right out of the box. System stability is not guaranteed, and a lot of disk images you find for use with full system mode, that is your file system, are relatively out of date. And it is because of these problems that Gem 5X was introduced. So what is Gem 5X? Gem 5X is an open source framework built on top of Gem 5 to simulate heterogeneous architectures, as well as a methodology to optimize said architecture. Gem 5X supports ARM full system mode simulations right out of the box with an Ubuntu 16 disk image and a precompiled Linux 4.15 kernel. Additionally, the minor, aka in-order CPU model, as well as the out-of-order core models in Gem 5X, have been tuned and validated against the ARM Juno board. So these models can be used to generate performance statistics representative of real ARM hardware. Other features of Gem 5X include a gperf profiler within Gem 5X, enhanced checkpointing, 9p over Virtio support, a validated HBM2 memory model, and others. In the demo section of this tutorial, I will cover how to use the checkpointing and 9p over Virtio support, as well as being able to maintain your disk image using chroot. As a tandem project with Gem 5X, I would also like to take this time to introduce to you my primary project, Gem 5 Extensions for RISC-V, or GXR5. All of the aforementioned features and enhancements in Gem 5X are targeted to the ARM ISA, but as open source hardware becomes more and more popular, there's a growing need for a Linux-capable, full system-level simulator for RISC-V architectures. Because RISC-V is entirely open source, it has none of the licensing fees associated with ARM. Therefore, the possibility of designing and fabricating your own hardware is much cheaper and easier than it would be with ARM. Unfortunately, though, full system mode support for RISC-V system-level simulations doesn't exist in Gem 5 nor in Gem 5X. And so it is because of this that we created GXR5. So the preliminary release of GXR5 implements Linux-capable RISC-V full system mode into Gem 5 using a Linux kernel 5.x and simple build root image. We are able to run a simulated simple board SoC based on the one introduced by Robert Scheffel's thesis and extended to model a simpler version of the Hi5 Unleashed SoC. It implements many of the missing architectural features required for RISC-V full system mode simulation, including missing instructions in both privileged and unprivileged ISA specifications, updated interrupts and interrupter models, MMU and virtual memory support, and others. So using GXR5, we are able to boot the Linux kernel and file system as mentioned, and then using this we are able to run basic benchmarks and unit tests. And finally, in a latest development, we were actually able to run a benchmark from the Spec CPU 2017 suite. Okay, so now that we've gone over the what and why, let's get into the how. I will start the demo shortly, which is split into two parts, one for Gem 5X and its enhanced features, and another for GXR5. In part one, I will show you how to set up and build Gem 5X, run your first simulation, and then how to use some of the enhanced features to optimize your workflow, including checkpointing and 9p over Virtio. In part 2, I will show you how to set up and build GXR5 and run your first simulation with it. As I mentioned in the beginning of this presentation, these demos are targeted for people who are relatively new to Gem 5, Gem 5X, and or GXR5. If you are not new to these frameworks but still want to see how you can extend these frameworks for architectural exploration and simulation, I would suggest again taking a long coffee break, and then we will see you at the next tutorial session. And finally, I just want to quickly mention that there are numerous resources available on the web for using Gem 5 in general, as well as the Gem 5X technical manual, which is listed here for reference. Okay, hello everyone. Let's get started with the demo. So as you can see, I have an Ubuntu virtual machine up and running, and this includes a lot of the downloaded files as well as environment setup you need for Gem 5X and GXR5. In case you are running this on your own Linux installation, though, of course, the very first thing you would do after downloading gem5x master.zip and fullsystemimages.tar.gz is you do something like a sudo apt-get install and then add in all of your dependencies. And these include things like Git, M4, scons, libprotobuf, Python, etc. In general, I would set aside maybe 10 to 15 minutes for everything to download and install properly, of course, depending on your machine and your internet connection. But anyway, as I mentioned, I already downloaded the Gem5X master zip file as well as the full system images tar.gz zip file. You'll also notice that I have a few other things in here for other demos, including gxr5.zip and rv full system images.zip. So in order to unzip and untar everything, you get ready to build Gem5X, you would of course do unzip download / gem5x master.zip, and if I hit enter right now, it would unzip into a new Gem5X master folder just in the current directory, in this case the home directory. So if I do ls right now, you can see I have Gem5X master already there, so that's all fine. So if I cd into Gem5X master, you can see that I've also untarred the full system images as well as created the build folder. These things would not be there in your folder after unzipping Gem5X master initially. To get the full system images folder, what you would do is tar/zxvf, and then go to your downloads folder, and then full system images.tar.gz, and hit enter. Keep in mind that does include a 32 gigabyte Ubuntu 16 disk image, which you will use for running Gem5X. And as a result, again, set aside maybe an extra 10 minutes or so to untar that folder, again, depending on your machine. So right, now that we have the Gem5X master unzipped, as well as the full system images, if I go into full system images, you will see that there's a binaries folder and a disks folder. So if I cd into disks and do an ls, you can see that this is the Gem5 Ubuntu 16 image. And if I do that, you see that it is indeed 32 gigabytes in size. And of course, not all of this 32 gigabytes is filled with stuff. This is just so if you wanted to add your own benchmarks and binaries and other things to it, you have the space to do so, including for things like the Spec CPU 2017 suite of benchmarks. And then in your binaries folder, you see we have several files here. This includes the bootloader, a couple of device trees, as well as VM Linux. Note that it is a requirement for Gem5 to run a static version of Linux, and that's what this VM Linux file is. This is in comparison to something like VM Linux, which you don't want to use for Gem5. So, okay, all of that said, we have all of our files unzipped, untarred, we have everything in the right location. Now what we want to do is run this apply patch.sh file. So in order to do that, you do /apply patch, and then the path to your full system images folder. So you could just do something like that. You could also do export M5 path equals whatever the path is to your full system images folder. Basically what this does is that this ensures that when Gem5 runs and it's looking for the disk image and VM Linux and the bootloader, etc., that it's looking in the right place. Otherwise, you're going to get system I/O errors when you start up Gem5. So, okay, now that we have all that set, if you've not installed ARM GCC, ARch, GNU GCC, and that sort of thing, basically cross compilers for ARM64 systems, you will need to do that now. So on this Ubuntu image, you would use sudo apt get install, and then like GCC ARM Linux GNU EABINF. Amongst a couple other things. Again, this is all listed in the Gem5X technical manual, so you can just copy and paste from there as you see fit. But basically, once you have the cross-compiler for ARM set up, now you actually do want to make your device trees that we're going to use for this, and in order to do this, you just do make-c system ARM system ARM DT. And, well, as you can see, I've already pre-compiled it, but usually you get a bunch of messages, and the end result, of course, is if I do system ls system ARM /DT, we have all of these DTB files. Now, these are all device tree binaries. They basically let the kernel know what hardware is on your system when you're actually running Gem5X full system mode. So for this demo, I'm only going to use the 1 CPU ARMv8 version of the device tree, but of course, if you wanted to run an ARMv7 system and run it with 8 CPUs, the device tree you would be using is like the ARM7 Gem5 v1 8CPU.dtb. So, okay, now that all of that is set up, you should be ready to build Gem5. And the way you do that is you do scons build /arm/gem5.fast. What this command does is it builds the gem5.fast binary. Keep in mind that there are actually 3 different kinds of binaries that Gem5 offers. One is fast, one is OPT, and one is debug. And the way you would build those is instead of having fast here, you would do OPT like so, or debug like so. Now, the main difference between these 3 different binaries is basically that if you just want to run benchmarks and you want to quickly get results, or get results as fast as possible, you want to use gem5.fast. However, if you want to use debug flags and maybe even put the Gem5 binary into something like GDB or Eclipse, then you do need to use the OPT and debug versions, which have less optimizations and therefore are slower to run. But for now, I'm just going to stick with fast. And then another tip you can use to make compilation faster is this virtual machine I'm running uses 6 cores. So I'm going to do -J4 to use 4 cores for compilation. And then as you see, we're going to get a lot of printouts here just checking libraries. And then it's going to check scon script files and check that everything is up to date and then compile everything. Now, I have pre-compiled this, so the compilation process, as you saw here, only took a few seconds. The first time you compile Gem5, expect it to take anywhere between 20 and 40 minutes or so. But after you've compiled it once, when you recompile it, you're only ever going to recompile the files you changed, basically. And so, as I just said, the first time you compile it, it will be slow, but afterwards it will be fast, just like you saw here. And then the end result of this is if I do ls build /arm/gem5.fast, you can see that yes, indeed, that file exists, and this is the binary we use to run Gem5. Keep in mind that the build process for gem5.fast, gem5.opt, and gem5.debug are completely different. So I've not built OPT in this virtual machine yet. So if I tried running it, the build command right now, it would indeed take that 20 to 40 minutes or so I mentioned. One other thing as well is that, as I mentioned previously, this build folder isn't here initially when you unzip the Gem5X master folder. You don't have to create it yourself. It will be automatically created by Scons when you build gem5.fast. Now that all of that is set, we are actually ready to run Gem5, and for that, in scripts I have run gem5x.sh. And basically, the script is what you see here. And so first, you're running the gem5.fast binary /d gem5x output. This is the folder that will contain the output of your gem5 run. The next parameter here is the config script. So this is basically, what does your simulated system look like? Like where is the hardware located? How is it connected to other pieces of hardware, etc. In general, we use fs.py for full system mode. You can create your own configuration from scratch. And there are tutorials online on how to do that, but for us it's just simplest to use fs.py because this sets up the memory controllers, memory buses, SoC devices, etc. And then CPU clock is, of course, the CPU clock, which is 1 gigahertz here. Here we set the kernel to VM Linux, which was the binary I showed off previously. The machine type we're just going to set to vExpress Gem5 v1. And then the DTB file, I do have a hard-coded path to. As you can see, we're going to run an ARM v8 system using only one CPU. And then this -n1 here actually specifies that only simulate one CPU. The next option is the disk image, of course, which is the same one I showed previously, gem5 ubuntu 16.img. And then afterwards, you have the caches and cache options. So it's here that you could set your own custom L1 cache size, L2 cache size, associativity, etc. And there are a lot of different options associated with this. And I can show off later where you actually find these options in case you want to build your own thing. And then finally, we have system clock and memory options specified as well. So in this case, we're simulating a DDR4 module at 2400 megahertz with a memory ring of 4 and a size of 4 gigabytes. So all of that said, we are ready to actually run Gem5X. So the way we do that is just bash run Gem5X using the script. You could type in all of this on a command line as well, and that would be fine. Of course, you'd just be typing a lot of things, which is why I have this script set up. This script is included with the virtual machine, by the way. And you can see the result of running it is that, you know, we get the copyright notice, the notice about compilation and execution. It tells you what exactly your command line is here. So if you have a weird option or you get a weird error later on that you think could be due to the system configuration, you can always double check this. And then you usually have a bunch of information or warning notices when the system is currently set up. And then finally, real simulation, meaning your simulation has started. So all of that said, Gem5 is now running. So if I open a new terminal, I can actually connect to the Gem5 instance as though it were another machine. And the easiest way to do that is to use telnet. So you do telnet localhost 3456. And you can see here that the kernel has already started booting in Gem5X, and these are the kernel D message logs here. So this is going to take a little while to properly boot up. In general, it can take up to an hour just to boot up the kernel and the file system, at which point you should be ready to run benchmarks. So I'm going to cut here and then come back when the login screen is up and ready. Okay, and now you can see that we've reached the login screen. And at this point, we can interact with Gem5 as though it were a simulated virtual machine like QEMU, for example. So I could type ls here, you can see it echoes out the command again, and we just have this one file, mount.sh here. I could also do like print working directory and use cwern/root. So one way I can stop it is to go back to the Gem 5 window where I initiated the run. You can see we got a few warnings here, but that's nothing to worry about. And you can also see that as we entered the login screen, we got this writing checkpoint message. Now, this is the first of many features in Gem 5X called enhanced checkpointing. So one way I can exit Gem 5X is to do Control-C here. And you can see exiting at tick this very large number because user interrupt received, and now Gem 5X is stopped. Now, if I go to the home directory again, you can see I have this Gem 5X output folder, and that's what I specified in the script I initially showed off. So if I go into that and do an else, you can see that there's several files here. These config files, which basically tell you what simulated hardware is in your system and what configurations you're using for them. This system.terminal file, which is basically the output that we saw in the other window. So if I do VI there, you can see it's like the kernel dmessage output here. And then we also have this stats.txt file, and basically what that is your performance statistics. You can track a lot of different things in Gem 5, but for example, if you're just worried about like how many seconds did it take to run your benchmark or something, you would just be looking at like this simulated seconds here, which in this case it simulated 152 seconds in total, even though the host number of seconds you can see was 818.4. And then the last thing you see in this output folder is all of these CPT files. And basically what these are checkpoint files. So Gem 5X is set up to automatically take a checkpoint as soon as you reach the login screen. And what that means is that it serializes the current state of Gem 5X so you can restore it later very quickly. Now, why is that useful? So say I wanted to run Gem 5X again and interact with the console some more, set up something or do something else. I don't want to wait another 800 seconds or so to reboot Gem 5X from the beginning. So instead, what I can do is I can go to scripts, and in here you see I have this run Gem 5X checkpoint.sh. And if I cap that right now, you will see that I added a couple options here. It's basically the same script, but I added this -R1 here. And basically what that means is run gem5.fast here with this configuration, but restore the first checkpoint you took. And now let me actually run this script, just so you can see the output. So you can see the normal Gem 5 binary start comes up, but then right now it's taking a little bit longer to actually get to real simulation. And there we go. It says entering event queue at tick this very large number. Basically what this means is that Gem 5 started at a tick much later than 0 rather than at 0. And if I go here to where my telnet connection was, you can see it exited out from the first instance being killed. But I can telnet again, and you can see I'm already at the login screen. I'm already at the command line. So again, I can do ls here and just interact with Gem 5 as I want. The way that checkpointing is implemented actually is through what's called the M5 binary, which is a way you can interface Gem 5X with the host machine. So you can see where it is actually in Gem 5X, just with the which command, and you can see there's sbin M5. And if for some reason I changed something here and I wanted to take another checkpoint, I could do M5 checkpoint within the Gem 5 window, and then it will make me a new checkpoint folder like we saw previously. And to double check that I did that, you can see this warning writing checkpoint is here in the Gem 5 window. So on the actual simulated machine, it does take a little bit of time to run the checkpoint, but once it's over, you see we get to the command line again. Now the M5 binary does come with a lot of features that I recommend reading the Gem5 documentation on, but like another one, for example, is instead of Control-C in the host window to stop the simulation, I could also do M5 exit just like that. Now, one of the most powerful features of the checkpoint feature is if I run this again, I can actually change some of these configuration options here. So, for example, the CPU model we're using in this script is the default CPU model, which we could actually double check just by going to the config file. So if I go here and I do vi config.ini, you can see this is what it looks like. And if I scroll down, you can see that we use the atomic simple model by default. Now, Gem5 has multiple CPU models, including the minor CPU model as well as the out-of-order CPU model. And where the real power in checkpointing comes in is the fact that the other CPU models would take a much longer time to boot the kernel with as compared to the atomic simple CPU. So you could boot your kernel and take your checkpoint with your atomic simple CPU, but then restore the checkpoint with, say, your out-of-order core CPU model. And then you can get performance statistics related to that O3 core model instead of this atomic simple CPU model, all while taking much less time to actually get your end result. Now, what can't you restore the checkpoint for? Unfortunately, if you wanted to change something in the disk image, you would have to start your simulation from scratch, basically. But there is a shortcut you can use to modify your disk image, or at least run different benchmarks and such without having to modify the disk image much quicker. And this is what 9p over Virtio enables. So to get started with that, you do need to install one dependency. So sudo get apt install, and then it's called diode. And then we enter the password for the conferences VM. And as you can see, I've already installed it, of course, but it's a relatively quick install. And then you want to do which diode. And you can see here that it's in user espin/diode. And to get started, you do need to update one file in Gem5x. So if I go to Gem5x master, and then I show source dev virtio and virtual io 9p.py. This is where the Virtio model is in Gem5, where it's defined, I should say. So you can see here we have the Virtio 9p diode class definition. And one of the options we have here is this diode equals param string user espin diode. Now in our case, I set this up previously, so I already edited this string, but in your system you may need to edit this string right here and save. And then after you've done that, you of course want to do a scons build arm gem5.fast. It's also worth noting as well that just rebuilding gem5.fast doesn't rebuild gem5.opt or debug, so if you wanted to use those after making this modification, you would also need to run the same command for opt and debug as well. But anyway, now that we have diode edited and compiled, we can go over to our next script and cat run gem5x 9p.sh. And so here is our gem5x running script again, where this time we changed a couple things. The big things we want to note here is the kernel has changed, and we've also added this workload automation option at the bottom here. Now, what changed in the kernel basically is that in order to use 9p over Virtio, we need a kernel that has the 9p module installed. So we've already compiled and distributed this for you. This is vmlinux_wa, which is in that same binaries folder I showed off previously. But then we also need to add this workload automation option at the very end of our script. So what this says is that we want to have a folder shared between the host and Gem5 at this location here. And you can see I set it at the home folder /script/shared. So if I do ls, you see I already made a shared folder. If I cd into the shared folder, I have one text file in here. Let's read it. It just says, "Hi there, HighPeak 2021." It's worth noting that you could put basically anything in here, say like a benchmark or another binary or another text file or anything. I just have this text file here just for demonstration purposes. But right, now that we have that all set up, we do what we did before, bash run gem5x 9p.sh. And unfortunately, this starts at the very beginning of the simulation run again. So, as usual, telnet localhost 3456. And now we basically wait for the system to boot up again, and then I can show you the 9p over Virtio features. Okay, and now that the system has booted up, you can see that we are at the command line again, as usual. If we go over to the Gem5x running window, you see we have the same warnings as before, but there's no issue there, as well as the checkpoint information. So if I go over back to our telnet instance, in order to use 9p over Virtio, we have to use this mount.sh file. So in order to use that, you do mount.sh and then the path to your shared folder, in which case this is home/conferences/scripts/shared. And we just run that in the terminal. And to double check that this worked, in the Gem5 instance, we do ls/mount. And you can see this test.txt file is here from before. And if I actually cap that to see what's in it, you can see that hi there, HighPeak 2021 file is there and intact. Additionally, I could go over to this third terminal window where I'm actually in the shared folder, and I could echo another message into a new text file. So if I cat test2, this one just says hello. Similarly, if I do ls/mount now, you can see test2.txt shows up, and I can cat it as well here. Cat it in the wrong folder. Cat it in the correct folder this time. And you see the hello is there as well. And so basically you can use 9p over Virtio to maintain your files on your disk image with relatively little overhead instead of having to restart Gem5x from right at the boot every single time. So, okay, all that said, we can now exit Gem5. And then the last thing I wanted to show before we call it for this part of the tutorial is just how do you maintain your disk image. Again, instructions for this are in the Gem5x technical manual, but really the best way is to use chroot. And basically what that does is that on your host machine, it allows you to remount your root using a static QEMU build. So you can basically update your disk image or cross-compile things as though you were on the native machine with it. And so to get started with that, you of course need to sudo apt get install a bunch of things. This includes QEMU, QEMU user, QEMU system, and QEMU user static. I already have those installed here, so we don't need to run that again. Just like before, you know, a lot may be like 5 to 10 minutes or so just to install and download everything, depending on your machine. But anyway, to get started with chroot, basically we go to Gem5x master, full system images, disks, and the first thing you want to do is sudo mount the disk image. So the command is a little bit complicated, but basically we're just skipping the boot sector of the disk image and going straight to the file system. So basically you use this command to mount this disk image, and of course you need to specify where to mount it, in this case /mount. And then if we do ls/mount, you can see that our disk image is mounted here. Now before we can use chroot though, we do need to bind several of the necessary folders to actually change over the root. And so the command you use for this is sudo mount -o bind, and then we're going to use this for a bunch of folders. So the first one is proc, so we do /proc and then /mount/proc. And then we also want to do this for /dev as well. So we modify this command just to /dev and /mount/dev. Then the next one is here, just modifying these. And then the last one we want to do is sys. So just modifying this command one last time. So we have /sys. Yep, there we go. And now we're ready to change root to our new root in the disk image. So in order to do that, we do cd mount, and then now we can do sudo chroot /. And you see now we're at root@conferences, and basically we're now in the chroot instance. We're actually in the disk image running it like it's our primary root. Like if I do an ls, you can see we have all the folders from before. If I do gcc --version, you can see that we're actually using an Ubuntu Linero 5.4 GCC version. And basically this means we've switched over to an AArch64 machine. And so from within this disk image, we can cross-compile binaries for benchmarks and whatever. You can also update and maintain your disk image this way. So like, for example, I can do apt-get update. We're already root, so I don't need to sudo or su or anything like that. And you can see I'm actually able to update the disk image files from here with no issue. And this can take like 5 to 10 minutes or so. This shouldn't take that long. So yep, see, there we go. So yeah, when you're done with chroot, you just type exit, or you can also do Control-D. And then to clean up your mount of the disk image, you need to unmount everything. So you want to sudo umount /mount/ everything we did before. So /mount/proc /mount/sys. You want to do /dev /pts before you do /dev. And then we also want to unmount /mount itself, but you can see that in this case it says we're busy, and the reason for that actually is because now we've cleanly exited the disk image. So yeah, that's everything I wanted to show with Gem5X. So now let's go over to the GXR5 demo. Okay, and so as we approach the end of this first tutorial session, I do want to quickly show off how you set up and run GXR5. Now, just a reminder, GXR5 is the RISC-V version of Gem5X at the moment, and it is still very much in a, let's say, alpha state. But it is the very first instance we know of being able to launch a full Linux kernel and file system in Gem5 full system mode for RISC-V systems. Now, if I go to the downloads folder, you can see, like before, we have a GXR5 zip file as well as this RV full system images.zip file. This is analogous to the Gem5X master as well as full system images tar file we saw earlier. So just like before, you would go to the home directory, do unzip downloads /gxr5.zip, and that would generate your GXR5 folder, which, as you can see, I've already done and already have this folder. So if I cd into here, Like before, I already unzipped the full system images folder, so we have this full system images folder you can see here, and then because I've pre-built gem5.fast and for GXR5, we also have the build folder as well. So as you can see, setup for Gem5 X and GXR5 is pretty similar, but there are a few key differences though, and it mostly comes from the full system images as well as the fact that it's a different ISA. So if we actually go into the full system images folders this time and we go into disks, we don't have an Ubuntu image, but instead a build root fs. This is an ext4 rootfs, but if you've ever used build root before, when you select the ext4 option, it actually creates an ext4 link to an ext2 rootfs because both ext versions are actually compatible with each other. And it's also a relatively small build root image, only being about 60 megabytes in size. Now, if you've set up and used build root before, you know you can just change an option and rebuild it, and you can get an image of different size, but this build root image works fine, basically. And then the other difference also comes in the binaries folder, where you see we have this forward jump.elf file, gem5 simple rv64.dtb, and vmlinux. Now, vmlinux is similar to the one before. It's a static Linux kernel file, this time compiled for RISC-V. The DTB file has been pre-compiled in this case, but of course, just like before, you would usually use the device tree compiler to compile your own device tree structure. And then this forward jump.elf file is actually the bootloader for RISC-V, and it's based off of OpenSBI. So, okay, all that said, we can go to the main folder, and just like before, in order to build GXR5, similar to what you would do in Gem5X, you would do scons build /RISC-V /gem5.fast, and just like with Gem5X, there's also OPT and debug versions as well, and the same J4 option works as well. So you can see you get same and similar output. Again, just like with Gem5X, slot 20 to 40 minutes or so of your time to actually compile GXR5 if you're compiling this for the very first time. But as I said, as I've pre-compiled it, Scons figures out there's nothing more to compile, so it only takes a few seconds to finish this. And the other major thing you need to do as well is you need to change your M5 path. Because GXR5 and Gem5X aren't integrated yet, you can't use the M5 path you used for Gem5X initially. You have to use the one for GXR5. So in this case, we're going to do export M5 path home /GXR5 /full system images, and that should set up everything. So now we can go over to scripts, and in this folder I have run gxr5.sh, and if I cat into it, you can see it's a much simpler system. Again, this is purely for testing and demonstration purposes, and we are adding more features as we go, but in this case we're running a single CPU RISC-V system with default L1 cache and 8 gigabytes of RAM. So in this case it's more representative of a small embedded system, which is quite common in the RISC-V space. You can also see we set the disk image to the build rootfs, as well as the kernel to vmlinux, and the DTB to this Gem5 simple rv64 DTB. So that said, we run the script similar to before, so run gxr5.sh. You can see there's our whole command line right there, and then we've already entered the real simulation. Just like before as well, we can also do telnet localhost 3456. And in this case, you can see that OpenSBI actually has an output initially, and we are running the Gem5 Simple Board machine platform. Now, as I mentioned during the lecture, Simple Board is an SoC first created by Robert Scheffel of the Technical University in Dresden. We use this simple board as kind of a jumping off point for creating our Linux-capable full system mode simulator. The simple board we extended has actually incorporated features from the High5 Unleashed SoC, which is or was the first Linux-capable SoC on the market for RISC-V devices. Of course, the High5 Unmatched has been announced recently as kind of a successor to the High5 Unleashed, and then I've also heard that the Beagle Bone Beagle 5, I believe it's called, will be released soon. So soon there will be a lot of different RISC-V Linux-capable SoCs on the market for you to play with, and you can use GXR5 to simulate them. Now, just like with Gem 5X as well, actually loading and booting the kernel will take a while. So in this case, I'll cut here and come back after everything is booted. But you can see right now that the first console Linux D messages have popped up. Okay, now that GXR5 is booted up, as you can see, we've got the GXR5 welcome message, and we're now at a command prompt. So again, just like with Gem 5X, at this point in Telnet, we can interface GXR5 just like we would in Gem 5X. Unfortunately, a lot of the features in Gem 5X are yet to be implemented in GXR5, but they will be coming soon. Things like the enhanced checkpointing and 9p over Virtio, things I mentioned. So for now, if you want to run a benchmark, say right at the startup of this system, what you can do is, well, first let's end the simulation with Control-C. Right, so what you can do is let's change directory to not Gem5X, but GXR5, full system images, and disks. And we can do sudo mount buildroot rootfs.exe2/mount. So we just mount the GXR5 disk image to our /mount folder. So if I do a sudo ls there, you can see everything from GXR5 there. And if we want to actually run something right at the startup, say like you cross-compiled a program or something, or you just want to double check something by echoing a text file, the easiest way to do this actually is to edit the init tab file. So in this case, I'm going to do sudo nano /mount /etc/init tab, just like that. And you can see this is what controls init for the startup of GXR5. So for the sake of demo, I have this RV hello binary that I'm just going to uncomment here. And you can see we just do the sysinit bin /RV hello, which is just this hello world binary I cross-compiled for RISC-V. So after uncommenting this, I just write it out in nano and then exit. And now I can unmount the disk image and go back to scripts. And now I can rerun GXR5 and reconnect to it with Telnet just like I did before. And I'll cut here as well and jump back to when we're on the login screen just so you can see the output of RV hello. Okay, and now that we're at GXR5, after it is booted, you can see this hello quarantine world message has now popped up. This is due to the RV hello binary running right at the start. If I run it again right now, you see it will print the same message again. Now, this can, of course, be swapped out with any binary of your choosing. In our tests at EPFL, we have used unit tests for this as well as spec. But for now, this concludes our demo of GXR5 as well as our tutorial on Gem 5X. And now we will open up everything to Q&A.
Okay, so here we are. Thank you for being there. So now I saw that Josh and David have been replying to questions on the chat and also the Q&A board. Are there any other questions that the audience would like to ask right now? Doesn't seem so. Okay. Okay, there's one question. Josh, do you want to take it? Josh, you're muted.
Just finding the question. Okay, can we simulate multi-core system using GXR5? So GXR5 is under active development at the moment. So we're working on single core system before moving to multi-core system. Though I suspect the move to multi-core will be rather straightforward when we do that. So I hope that answers your question. Let's see, next question is, for the build root images, do you then mount and copy over the M5 binaries after creating the image? Yes. So for all Gem5 images, you typically have to make the M5 binary and then copy it over to your system before you can use it. Obviously, when you make a disk image from scratch, Gem5 is usually not a consideration. So in Gem5X, we of course have the make file already there for you to make the M5 binary. When we do release GXR5, there will be one for the M5 binary for RISC-V in particular. And if you look at other versions of Gem5 for, say, like x86 or Alpha, there are also compilation tools for those M5 binaries as well. So I hope that answered your question. And then the last one is SMT available? I assume you mean simultaneous multi-threading. No, this is not available, not in GXR5 nor Gem5X, I don't think, because SMT is an x86 thing, if I recall correctly. But somebody can correct me if I'm wrong there. So, okay, I think that was all the questions.
I think that's it. Well, in any case, so what we have in our program for now is now we are going to do one coffee break. So we scheduled 30 minutes of coffee break until 4:30 because we assume that some of you guys will probably still be working and typing on your virtual machine. So that's why we extended the coffee break in case you want to give it a go at everything we said on your own. And then we will reconvene at 4:30 and we'll go for the second half of the tutorial. Just don't, I will leave in any case the Zoom open. So if you have questions during coffee break, after coffee break, whenever you want, just type them either, so try to type them on the Q&A if possible so that we can keep track of what we have answered and what we haven't. We're also looking into the chat from time to time. And basically just keep on typing, keep on asking questions. Either we will solve them written if it's easier, or we will basically just do as Josh just did, reading out the questions and solving them, okay?
So before we go to coffee break, I do see there's one more question just in the chat, which is, where is the GXR5.zip download link? So we've not released it yet with this virtual machine, but I think as Marina stated in one of the earlier sessions, if you want access to kind of an alpha build of GXR5, send me and her an email, and we will give you access.
Yeah, we'll basically, as Josh was saying, it's not yet available on GitHub because it's still in too much of an alpha state to be able to open source it to everybody, because I believe people will just have a lot of questions. But given that you have been following the tutorial and that you will be able to replicate everything because you saw how we are doing it, if you want the gxrx.zip download link, just send us an email and we'll share it with you. So I don't see any further questions. So, okay, let's then close for now. And in 30 minutes, we come back. Just type your questions whenever you have them. See you in a bit. Thank you. Okay, so let's restart the session. I see that there are no open questions on the Q&A board. If you have questions, just keep on writing. There has been a bit of conversation on the chat, but that's it. Okay, then we will go for the second half of this hands-on session, which would be on the optimization of architectures using Gen5X. So again, some methodology. I'll be playing a video. It will be like around 30 minutes long. So basically, just keep on posting questions. And also after this last video, you will have plenty of time to ask anything you want and to solve all your doubts. So let's go for it.
Hello everyone, welcome back if you attended the first tutorial session, and welcome if you're just joining us now. So just to recap, in the first session we introduced Gen5X and provided a hands-on tutorial on how to run and use Gen5X. We also premiered GXR5, our RISC-V extension for Gen5, as well as covered some useful features and techniques. In this session we will focus on optimizing and extending architectures with Gen5X and GXR5. In particular, I will demonstrate extending the ARMv8 ISA in Gen5X, as well as discuss how you can also do the same in GXR5 with the RISC-V ISA. In addition to that, I'll also discuss adding devices to your SoC after you've extended the ISA. So first of all, why would you want to extend the ISA to begin with? In general, ISAs have unused opcodes that are left open for new extensions. This gives us room to enhance the capabilities of our CPU with new and specialized instructions, such as through the use of a new functional unit or accelerator. It is also important to compartmentalize extensions in RISC ISAs like ARM and RISC-V, because small embedded systems trying to meet cost and power constraints may not need advanced capabilities such as vector extensions or even floating point. On the flip side, high-performance systems using these RISC ISAs may require the aforementioned extensions for high-level applications and benchmarks. All that said, if you're familiar with HDL or other low-level modeling methods, the idea of extending an ISA for your research may be a little bit daunting. For example, for every CPU model you want to explore, you will need to modify its decoder as well as numerous other components, potentially on a per model basis, depending on your extended ISA's capabilities. Of course, there are methods you can use to reduce the overhead of modeling your ISA extension in HDL, but in Gen5, it is actually incredibly straightforward. So what you need is simply your new instruction definition, an idea of your new instruction characteristics, and at the end of the day, you only need to modify 7 files in total to extend your ISA plus 1 or 2 additional files per CPU model you want to extend the ISA for. Basically, the way extending ISAs in Gen5 works is to first add statistics tracking for your custom instruction to the base CPU model. Second, add the new functional unit to your CPU model. Third, define the instruction and functionality in your ISA microarchitecture. And 4, recompile Gen5. And that's it. So for a hands-on example, let us now add a new instruction in Gen5. In this example, I'm going to walk you through the add1 test that is included with Gen5X and described in the Gen5X technical manual. This toy example sets up the basis for which you can simulate new accelerators integrated as functional units within your CPU. The instruction we are adding here is add1 in the ARMv8 ISA. It is the same as the add instruction in the same ISA, but it uses an unused opcode. Note that the steps I outline here are going to be the same for Gen5X as they are for GXR5. The primary difference is that in GXR5, instead of using ARM ISA files located in source Arch ARM ISA, you would use the RISC-V ISA decoder in source Arch RISC-V ISA. In addition to that, of course, the actual instruction format differs slightly, but it is actually much simpler to modify the ISA in RISC-V, so this example will prepare you for both. As one final note as well, it is exactly this toy example that established the basis for the binary dot product engine paper published in VLSI SOC 2019, as well as current research projects that I am working on. So not only can you use this example for architectural exploration, you can publish with it as well. The files you will need to modify are listed here. Essentially what you are adding here is a new instruction type that can be tracked in the Gem5 statistics file at the output of your Gem5 run. In the inst.proto file, you are simply adding an index for your custom instruction enumeration. In the execcontext.cc file, you are adding the stats variable that tracks how many times the instruction was called. And finally, in the base.cc file, you are adding the statistics name and feature to the stats file for Gem5, as well as incrementing the stat every time the instruction is run. The next step for adding this new instruction to Gem5 is to add the functional units to our CPU models. For the base CPU model, we add the op class name in both functunit.py and opclass.hh. This will be the generated C++ class for our new custom instruction. Now we need to add this functional unit to our CPU models. First, in the minor CPU model, aka the in-order core model, you want to make a child class that uses our aforementioned op class definition, as well as add this new functional unit class to the functional unit pool. Note that this oplat variable is where you would set the number of cycles it takes to perform this operation. So if you were implementing a custom instruction that does a lot more than add, and you found in your preliminary test that it should have an op latency of, say, 12 instead of 6, you would just modify this number here. After you've done this, we can now modify the out-of-order core model. Similar to before, you want to add a child class that uses the aforementioned op class definition, as well as add this new functional unit class to the functional unit pool. The O3 model separates these into two files, so you just add the custom ALU to default fupool and fupool.py, and then the custom ALU class definition to functional unit config.py. Just like before, you can set your op latency in the fu class definition here, but instead of having a separate variable for it, you use an argument in the opdesc instantiation. The count variable here is the actual number of functional units dedicated to the custom ALU in your O3 core model. The next step is to now actually extend the ISA. For ARM, this requires that we modify two files in the Gem5X source arch ARM ISA folder. Note that for RISC-V and GXR5, you would only need to modify the decoder file in the source arch RISC-V ISA folder. Note that these .isa files that are listed here are actually in Gem5's domain-specific language, or DSL. However, the Gem5 creators were smart enough to not make something so complicated as to require learning a whole new language. You can basically treat definitions as Python-like code and implementations as C++-like code. So in arch64.isa, we are defining how our instruction is actually decoded, as well as the existence of a pointer to the instruction class. In our case, our custom instruction has bits 27 to 30 set to 0, and then bits 23 to 25 set to 2. So it is here that we return our new custom instruction object. Note that as you can see in the code around here, there are a lot of return unknown 64 statements. This basically leaves you room to implement multiple custom instructions if need be, in case you wanted to implement 2, 3, or even more instructions instead of just the single add one. Then in data64.isa, we actually define the functionality of our new instruction. ARM actually gives us helper functions to define new instructions with. This build data instruction uses one destination register, dest64, one argument register, op164, and then an immediate sec-op. Note that if you wanted to use, say, a multiple register argument instruction format, there's another helper function called build.dataxreginst for that. This same file, data64.isa, actually has numerous examples of the various helper functions you could use to extend your ISA in many different ways. But anyway, as you can see, this is where we add our instruction functionality, as well as the instruction mnemonic and the op class that we had from before. If you wanted to change add1 to, say, add an immediate value in a register and 1, I would simply do desc64 equals restemp equals op164 plus secop plus 1 semicolon. As I said before, this is basic C++ code, so you could really do whatever you like here. So anyway, that's it. At this point, our custom instruction is implemented, and all we have to do is recompile gem5, and you're ready to use the new custom instruction. So you may be asking yourself at this point, I have this in custom instruction now, but how do I test and use it? How do I know that I actually did everything correctly? Thankfully, this process is relatively easy as well. To test our new custom instruction, all you will need to do is use some inline assembly. In C/C++, this is easy because you can just use the built-in ASM method. Here I have pictured from the add1 test example the exact ASM you would use for this instruction. We take out input to this function in1 and move it into register x9. The custom instruction is then run using both x9 as the Rn input and the Rd output. The result is then retrieved from register x9 and placed into this result res variable and returned for whatever high-level function we want to use it for. So now that we've done everything here, I will quickly go over to my virtual machine and demo this in action. All right, let's get started with the demo. So in the VM, if I go to the downloads folder, you can see that I have a modified files folder and associated zip file, as well as an add1 test folder and associated zip file. In the modified files folder, you will see that we have all of the files I previously mentioned in the lecture, all modified to add the custom instruction, as well as this modified file list file. In the file list file, you can see the actual locations for all of the files. So a simple way to implement the custom instruction from the tutorial is to simply copy all of these files to the associated locations in Gem5x. Just a note, if you do get an argument definition error or a function definition error, when you rebuild Gem5, that is referring to source simple base.cc. Basically, there's an inconsistent function definition on line 476 of base.cc and source CPU simple. If you just copy the argument from the associated function in base.hh in that same folder, that should resolve the error, and you can rebuild Gem5 again. So that's everything in modified file list, and in this case, I did indeed just copy all the files over, rebuild Gem5, so that is all ready to go. In addition to this, I have the add1 test folder, which contains the code, a compilation script, as well as the binary for this code. Now, if I cat add1 test.cpp, and I scroll up, you can see the same addition function I showed off in lecture, where we take this input in 1, move it to register x9, run our custom instruction with x9 as both our input and output register, and then move the output that's in x9 to whatever our result res is. So we took this function and we put it into this main, where you can see we declare one array of 10 integers, 10, 20, 30, 40, etc. And then we have a for loop where we copy the values of this array into a new array, but we also apply this addition function. Now the custom instruction up here has the immediate hard-coded to 3. So if this C program works as intended, basically C should contain the values 13, 23, 33, 43, etc. Now, to demo this, what I'm actually going to do is use 9p over Virtio to access the add1 binary in the shared folder. So if I go to scripts, you can see that I have this run gem5x add1.sh that actually restores a checkpoint from the 9p over Virtio demo. And if I do ls shared, you can see the add1 binary is indeed right there. So to get started with this, I will do the run gem5x add1.sh, which you can see in the command line is the same as the 9p over Virtio demo script, except I add this restore the first checkpoint variable. Now keep in mind I already copied over the custom instruction files, I already recompiled gem5, so this is running with the custom instruction right now. And then to actually run the demo program, I will do telnet localhost 3456, and you can see we're already at the command line. So now I'm going to do sh mount.sh home/conferences/scripts/shared, basically the location on the host where our add1 binary is going to be. And just to make sure it works, when it's done running, I'm going to ls/mount. You can see that gem5 does indeed have access to this folder and add1 does exist. Now, if I do ls/al, sorry, not in the current directory, if I do ls/al in /mount, you can see that add1 does indeed have read, write, and execute permissions on it. Note that if you just copied it over directly and you didn't change anything, you might see that it only has read and write permissions on it, in which case, just from within gem5, you do chmod 777/mount/add1. And that would ensure that you could indeed run the add1 binary. So that said, let me actually run it now. And you see, yep, as 13, 23, 33, etc., all running the custom instruction. Now I can do an M5 exit to exit the simulation. And then next what I can do is actually go to the output folder for this later run, so latest run, I mean. So if I do cd gem5x 9p output, you see that we have all of our checkpoints, our config, our stats, etc. And now I want to open the stats file, and I'm going to do a search for cusalu. And you can see that from our output statistics, the system CPU op class cusalu ran 10 custom instructions as expected. And right, so that concludes the demo for the custom instruction extension. So now that we know how to extend the ISA in gem5/gxr5, we naturally want to better understand our limitations of our simulation. The primary obstacle that arises from implementing an accelerator in this way is the need to use non-volatile data structures. Even in the binary dot product engine paper, kernels were selected from memory, then used to perform the convolution. Now, there's multiple ways to go about implementing non-volatile data access to our instruction. One method could be to use a memory load type of instruction to actually load stored data from memory or storage. This would require using a different instruction format, and the implementation in Gem5 would be slightly different than what I outlined previously. Another method could be to simply hard code non-volatile data into the instruction definition itself. Recall that in the data64.isa file, we simply use C++ to implement the functionality of our add1 instruction, i.e. we use a constant array to access hard-coded values. The method I will describe today, though, to handle non-volatile data structures through custom instruction access uses SOC devices. SOC devices in Gem5 are objects separated from the ISA. By establishing a common interface, you could add a custom device to your SoC and then access it via your custom instruction. One note I should mention here, however, is that all of these suggested implementation methods are viable for different kinds of architectures and applications depending on what you want to explore. There is no best answer here, though in my opinion, however, adding a SoC device is the best method when you want true ISA and device separation for applications where you may have more than one way to access your accelerator. So in this follow-up demonstration, I am going to use our add1 custom instruction enabled system, but offload the add1 functionality to a custom SoC device. Just like before, the concepts and implementation here in Gem5X are applicable to GXR5, but it is inevitably simpler in GXR5 due to a simpler SoC configuration. So as you can see here, we will keep the same instruction definition, as well as the same instruction assembly and format. But to show the capabilities of this new SoC-enabled instruction, I'm going to modify the instruction's function to return the sum of Rn and your immediate value and this ++ x variable. In this case, x is going to be a variable held in the SoC device that increments by 1 every time the instruction is called, and is subsequently added to RD. The way I will implement this device is as a custom peripheral I/O or PIO device sitting on top of our ARM RealView platform. So to show roughly what the system configuration will look like, I have a diagram here showing the CPU model, SoC, and the bus that connects the two. Over here is the CPU model, where at some point within its pipeline there is an execute stage that can run the custom instruction. And on this side is our SoC, which houses the peripherals, including our custom device for the add1 instruction. Now, while we could use the I/O bus to interface the device, what we'll be modeling here with our add1 custom device is a direct line between the CPU and device, which I have highlighted here. Since we won't be using the shared I/O bus, we can model very fast response times between the device and the CPU. Now, implementing this device does take a bit more code than the ISA extension example, but it is still relatively straightforward. I will cover the high-level implementation details, and then the rest of the code is provided for you. So, the steps required to implement an add1 SoC device are as follows. First, we have to create the C++ device model and implement its methods. Next, we have to use Python to add this device to our SoC configuration. Then we will use the Gem5 system object to add a connection between our custom instruction and the SoC device. And finally, we just recompile Gem5 as before, and that's it. So for the first step, we need to add the new device. We implement the new device in C++ using a header and associated implementation file, in this case, custom device.cc and HH. In general, all device models in Gem5, ISA specific or not, are located in source/dev. Here I have pictured the header definition for the custom device class. As you can see, it inherits from the basic PIO device class, which has some required methods which are at the bottom there. The most important parts of the class are the private variables and the add method. The ARM system object is a pointer that will allow the custom instruction to interface the device directly and vice versa. And then the integer x is that non-volatile variable we are demonstrating. And finally, the add method is what we will call in the custom instruction to produce the result. To ensure that the device is built into our system, we also need to add the implementation file to the list of sources in the scon script. This will tell the build system to compile the custom device along with everything else. You'll also see here that I added a debug flag for the custom device. If you are aware of Gem5's debugging utilities, this is where you add that flag. If not, I would be happy to discuss and go over it during the Q&A. Next, we need to add our device to the system config. Since we are using ARM and Gem5X, this means adding our device to the RealView platform. Note that in GXR5, you would be using RISC-V and the SimpleBoard platform for this, but the process is pretty similar. It is in this Python file that we both define the existence of the custom device class, as shown here, as well as add it to the RealView platform itself. And then there are a couple other methods not shown here where you would add it to a list of peripheral I/O devices, which are then used by ARM's predefined helper functions. And finally, before we compile Gem5, we need to interface our custom instruction through the system object. First, we add both a self-referential system object and custom device pointer to our system object. The custom device uses the self-referential object later during the instantiation of the whole system. Then in our ISA includes file, we add both the system and the custom device headers, which will ensure that these header files are compiled as the new instructions are generated. And finally, we adjust our custom instruction definition to use our custom device. As you can see in the code here, through the system, we get a pointer to the custom device, and then to get the result, we use the pointer to the custom device and call its add function using op164 and secop, aka the immediate, as the arguments, and then store the result in desc64. So then to test our custom device integrated with our ISA extension, we will use the same test program as before, where we send an input to register X9, call the custom instruction, and then retrieve the result from register X9 again. So allow me to jump to the virtual machine now for the demo. All right, now for this last demo, let me go over to my downloads folder, or files again. You see I have this modified files SOC folder and associated zip. So just like the previous demo with modified files SOC folder has all of the files you need to modify in it, in addition to those that you already copied over from the modified files for the add1 test and the extended ISA. So again, an easy way to implement the custom SOC device without jumping through all the hoops of figuring out every little bit of the code is to simply copy all of these files to the specified file locations. And of course, the specified file locations are in the modified files list, as you can see here. So that said, just like before, I copied over all these files, I recompiled Gem5, and then I ran it using one of the scripts in the scripts folder. So you can see here, I ran it from the start, didn't have any errors except for the usual warnings. And if I go over to the telnet window, you can see I'm at root at localhost again. So if I do sh mount.sh again, /home /conference /grip/shared. Oh yes, this is the 9p over Virtio version of Gem5X running right now. So if I do ls/mount, you can see the add1 binary is there just as before, and if I do ls-al/mount, we still have permission to execute it, which is good. So remember before that the add1 code basically had us copying values from one array to another and adding a hard-coded immediate of 3 to each of those values. So 10 became 13, 20 became 23, 30 became 33, and so on. So in this case, we're also adding this variable x, which is being held in our SOC device. And we're incrementing x every time we call the instruction. So in this case, for the first time we call the instruction, 10 will turn to 13, but then 13 plus 1, so it becomes 14. The next time we call the instruction, 20 is going to become 20 plus 3 plus 2, because we incremented x again, and so on. And so if I run /mount/add1, we should see this pattern realized. And indeed, that's what we see. The first value is 14, then 25, then 36, then 47, then 58, etc. Now at this point, because we've run the custom instruction 10 times, x should now be 10, which means if I run this again, c at 0 should actually be 24, because remember, we're still copying over an initial value of 10 and adding the hard-coded 3 from the custom instruction, but now x is going to initially be 10 instead of 0. So if I run this again, you can see, indeed, C0 is now 24, C1 is now 35, C2 is now 46, and so on. And if I run this yet again, now it's 34, 45, 56, and so on. So this is how we know that the non-volatile storage capabilities of the SV device are working as intended. And so at this point, I think we're ready to open it up to an extended Q&A, and thank you everybody for coming to HighPeak, and thank you all for your time.
Well, thank you everybody for being there. I think that Josh has been solving questions as they have been appearing. In any case, we have now some more time for an extended Q&A. In case you want to raise some point, discuss something, just don't be shy, just put your questions on the Q&A pane or on the chat. So are there any questions from the audience that you would like to ask? I don't see anything so far. Let me, while you think about questions, or let me just clarify that. So all the sessions, all the full session from the morning until now has been recorded. So HighPeak will make available all the recordings to the participants. I cannot tell you if it's going to be right after a tutorial or if it will be right after HighPeak. But basically, I have all your emails because I have access to all your emails, and I will keep those in order to be able to send you an email once everything has been posted and to tell you how to access that. Okay. So basically, HighPeak or HighPeak organization will post this on social media, but ourselves, the organizers of this tutorial, we will also post the so that you can check them one by one in an easier way. So just keep in mind that our goal in this is that you can replicate everything we have done. So it's not only a matter of you listening to us today. We understand that the benefit of this tutorial is also for you to be able to, you know, after a while, once HighPeak is over, to just go and be able to run everything we have tried to run and to fight yourself a bit against Gen 5 and Gen 5X and GXR5. So don't be worried. We'll try our best so that you can have access to everything we did today so that you can replicate. So any further questions, things that you would like to say? Okay, so we have one question on the Q&A. Can you point to some useful resources for Gen 5 that can help implement new features to Gen 5? Josh, maybe you can take that one, because I think in one of your slides, you basically had some resources. Is that correct?
Yes, so there are numerous resources for learning various aspects of Gen 5 out there. You'll find a lot of it either in YouTube videos or on the Gen 5 website itself, which is gen5.org. There's also the Gen 5 mailing list that you can subscribe to, also on gen5.org, where you can generally post questions and go through archives of previous questions to figure out different aspects of different parts of the Gen 5 system. And keep in mind that is for Gen 5 in total, not Gen 5X in particular. If you do have particular questions for Gen 5X, I believe there are mailing lists that Marina maintains. And then for GXR5 at the moment, we just have Marina's email and my email. But once that is released publicly, we'll have mailing lists for that as well.
Just maybe you can go on with the questions. Sounds good?
Yeah, I see a couple more questions. Thank you for the talk. It was extremely interesting. In terms of ARM simulations in general, do you have any experience and or advice for using ARM PMUs in Gem 5? So that is ARM performance monitoring units, I believe. Correct me if I'm wrong, of course. For that in particular, I believe those are already included within the RealView platform in Gem 5, which is to say that these performance monitoring units are already incorporated in the base Gem 5, and you can use them more or less like normal.
Yeah, my answer to the question is the same. Thomas, in case we are not answering what you want, or in case we didn't understand the question, just retype, because I'm not sure if we properly answered, but I had the same answer than Josh, in fact.
Yeah, so you can of course double check by just going to source/dev/arm, and what you'll want to look for is the realview.py file. That file contains basically the definition for the entire SoC in Gem 5X for ARM systems. You'll see that there's a lot of different platforms on it, and which one you use changes, but it should be listed there, I think. So, okay. Unless there's a follow-up to that, I'll go to the other questions. So the next question is it feasible to simulate a small RISC-V SoC minimal ISA support connected to an ARM/x86 CPU in Gem 5, Gem 5X, or GXR5? Should every instruction be defined the same way as add one in this tutorial? So heterogeneous ISA systems, I don't believe have native support in Gem 5 or Gem 5X or GXR5, unfortunately. The only heterogeneous ISA-ish system supported by Gem 5 is the no-moly GPU model, which is a ARM GPU model, basically. And that's included in both base Gem 5 and Gem 5X.
Yeah, and also the closest thing to that would be also, so we can simulate also ARM processors, that is in order cores with out of order cores in the same. In Gem 5, if I remember correctly, if you try to run that directly on Gem 5 without Gem 5X, it doesn't work because there are some tips and tricks that you need to apply. But if I remember correctly, in Gem 5X, we fixed that, and it works also. But that's the closest that you can simulate. What Josh said, and these big little architectures is the closest you can simulate to a multiple ISA system.
Okay, and then for the next question, how accurate are the ARM cores simulation? Can it be compared to ARM fast model? So I'm not sure what ARM fast model is, but as Marina covered in her lecture, Gem 5X has validated core models that get you performance statistics within 4% of the real hardware. So if ARM fast model is like an RTL simulation or something, you can expect accuracy within that 4% margin, I think. But let me know if that answers your question. Okay, and then I see another question, or I see a response to, I'll look at the response to Thomas Hansen's questions first. Thank you for the answer. I've been having some issues getting them to work, and looking at source arch arm pmu.cc, there seem to be a number of to-do items. So I'm wondering if there is any tricks to getting it working. I would say write me an email and I'll ask around some coworkers, because I'm not super familiar with the PMU, but my colleague Yasir might have gotten it working for one of his previous projects. But thanks for double checking that. And then, okay, we have another follow-up. Fast model is proprietary simulation model by ARM. Okay, thanks for letting me know. Okay, so let me get to the other questions then. How complex can be the new custom instructions? Are there any limitations, aspects that cannot be described? For example, can I describe ZOL, zero overhead loop? I'm not familiar with ZOL, so you're going to need to explain to that one with me, but as I described in the talk, the actual implementation of the instruction is just straight up C++ code. So anything you can think to do with C++ code is doable. Depending on what you want to interface specifically in Gem 5, it can get more or less complicated. And that's also dependent on like how efficient you want your simulator to be. So basically what it can't simulate is like, for example, having multiple instructions run in the same instruction, basically like you trying to define a macro op within a single instruction. That's not doable. You do need to actually split into nano ops, and I guess that's more applicable to x86 systems. If you let me know what a ZOL is, I can probably be a little more specific with that answer. And then another question is, can heterogeneous cores be simulated with Gem 5, like an ARM dynamic IQ? So like as we described previously, like if you wanted to do like a multi-ISA system like ARM Big Little, that is possible in Gem 5 actually.
In fact, just to complete that ARM Big Little script is the one that I believe was not totally working if you download the vanilla version of Gem 5. That's the one we got issues with. But if any of you guys wants to give it a go to the Big Little configuration and it doesn't work, or you have issues with that on Gem 5, again, just write us an email. Because we managed to sort that out, so we can give you some details of what we did exactly, what's the magic we did behind. Questions from the time being on the Q&A pane or on the chat.
I do see in one of the chats, are there any publications related to Gem 5X? So yes, Gem 5X has its own paper as well as another journal paper coming out soon, I believe. And then as far as publications that use Gem 5X, of course, Marina covered the Blade example in earlier lectures, which was published in 2019. And then for my lectures, I covered the binary dot product engine, which also uses Gem 5X, as well as like the ISA tutorial I presented specifically.
In any case, once we can share our slides with you, which will either be done either through HighPeak or through our own media channels right after the conference. So in the last slide of our talks is normally all the references and publications related, and the related publications. So you will get a list of all those. Just to complete that, what we will be also doing is to, so that you have our contacts, because maybe you missed it and maybe it's not easy to remember what are our emails, etc. After the end of the session, we will send you an email where you will, so that you have my contact, so that you have Josh's email also in case you want to reach out to us. And basically in that way, we will also have your email so that we can keep you updated on when, where, and how you can access all the recordings and all the slides. Okay, so I see no more questions. Josh, is there anything else you want to say?
At this point, I guess thank you for attending my talks. Thanks for attending HighPeak. I hope this was incredibly helpful, but as Marina said, if you have any lingering questions or thoughts or things you want to discuss, our emails are going to be in the slides, and we'll post them to you as well. And we'd be happy to open conversation channels with you. And then kind of like the very, very last point, I guess, is that, again, GXR5 is an alpha state, but if you do want access to it, you are interested in collaborating with it or using it, again, just send Marina and I an email.
Okay. Yeah, so on my side also, thanks for everybody. Thank you, everybody, for participating in this tutorial. As Josh said, we really hope it was useful for you. We know that the important chunk is to give you back, is that you get access to everything afterwards so that you can repeat it with your computers next to it and, you know, trying to type everything. Don't worry, we'll share everything with you. And then let's then close for today with this big thank you. And hope to see you soon. Hope to see you in HighPeak next year, physically, you know, these kind of things that we don't do anymore. Yeah, so I hope to be able to see you face to face in next year in HighPeak or in other HighPeak editions or other conference. Thank you all for attending, and you'll be hearing from us. We'll send you emails so that we can keep connected. So thank you, everybody, and have a good day and enjoy the rest of the HighPeak conference. Thank you.
Thank you again, everyone.